Good day, everyone. We're about 10 minutes from the top of the hour. At this time, could I get actually a sound check from Kathy?
Good morning. Can you hear me?
Yes, I can. Great. Thank you.
Recording in progress.
We're just about at the top of the hour. And so at this time, I'd like to let everyone know that this session is being recorded. And we can go ahead and, Alice, you can go ahead and get your first presentation up, and I will hand it on over to our chairs today.
All right, good morning, everybody. I am Kathy Mont of the Johns Hopkins Applied Physics Lab, and I'm very pleased to have the opportunity to chair this session with Elizabeth. Elizabeth, if you want to introduce yourself.
Hi, my name is Elizabeth Fisher. I'm currently a grad student at Brown working with, sorry, my phone is, I have a million alarms because the session is starting. I work with Jack Mustard and Carly Peters on lunar volatiles, and I'm very excited to be here. I think we have a great line of talks and we're going to have a great discussion.
Yes, I think we will. So this session is a mixture of oral presentations that are allocated 10 minutes, including time to transition to the next speaker, and then poster lightning talks that are allocated 2 minutes, including time for transition. So what we are going to do for the 10-minute talks, we will give you a 2-minute warning so that you know that it's time to finish up. Also, Elizabeth will have the background for the timer available so that you can also watch that and see how your time is going. We will save the questions for the end and the discussion time period, and we encourage you to use the chat. If you have a question, put brackets with a Q and type your question. And we will have the opportunity to have discussion with all of the speakers at the end of the session. We want to remind everybody to be mindful of the code of conduct, that that applies to all presentations and to the discussion, both orally and in the chat. And we will get going. I'll hand it over to Elizabeth for the first speaker, to introduce the first speaker.
All right. So first off, we have a talk by Alice Stefant about the deuterium poor water source for the moon and the early Earth. Take it away.
Yes, thank you very much, Elizabeth. So today I'm going to start the session by talking about the water inside the moon. Alors, up. And so in fact, it's been a little bit more than 10 years that we know there is water inside the moon, thanks to the pioneer works of Alberto Sal and co-authors in 2008 on lunar volcanic glasses. Since this time, the lunar volatile community has tried to infer the abundance of the water and also the source for this water inside the moon interior. And the question has been raised, like to know if the water came from the early Earth or from Theia itself, or if the water was brought later on by some influx of carbonaceous chondrite. And in fact, all of these questions bring a lot of implication for the formation model of the moon. And so to try to infer the water source for the interior of the moon, we use the hydrogen isotopic composition, so can be not in delta D ratio or in delta D, per mil or in DOH ratios, the horizontal line here. And you can see that the range here in gray for the moon should match the one of its source. So far, it seems to match the terrestrial value and some of the carbonaceous chondrite. However, you can see that the range for the moon is very large, between -300 to +300 in per mil, and it has not been possible yet to establish a very precise delta D value for the moon. And this is due to the fact that there is a huge heterogeneity in hydrogen among the different lunar reservoirs. We know that from the study of various targeted phases, so volcanic glasses, melt inclusion, apatites, and plagioclase that has been studied with the secondary ion mass spectrometer. For instance, here we have a compilation of data, so H2O versus delta D in per mil for apatites. And you can see that mare basalt, so low TI and high titanium in blue here, share a cluster of H2O delta D signature, which is highly different than Mg and alkali sweet here in orange, in yellow, and the creep-rich evolved lithogy here in green. And so we try to understand the source of this heterogeneity among the lunar reservoirs. And one hypothesis is that there was a global scale degassing of hydrogen during the crystallization of the lunar magma ocean. But as of today, there is not really direct evidence of this degassing, and this is what we are trying to test with this new study. So we have studied nominally anhydrous minerals, so both pyroxene and olivine in 8 Apollo samples that cover the range of lunar lithologies, so high titanium basalt, low titanium basalt, high aluminum basalt, ferro nanotosite, and Mg sweet norite. The advantages of studying NAMs is that they are large and abundant in all Apollo samples. They form very early, which means that they are less prone to degassing of hydrogen. However, it was a very challenging measurements because they contain very low water content. And so there was some problem, obviously, for controlling the contamination of terrestrial water, and also to correct for the spallation contribution of deuterium. But most of the sample, almost all of them, had an exposure age lower than 50 million years old. And so if we start here from the lunar magma ocean, before any crystallization, so we infer a delta D and a H2O initial that we don't know, but this is what we are trying to know at time 0. And we start to crystallize. And we're going to replace the various linear lithology that we study in here into the cumulate of the crystallization of the lunar magma ocean. So first, we are going to crystallize the primary material. So the source cumulate for the norite 77215 here in purple, and the high aluminum basalt 14072. As you can see, they have quite low but relatively high water content between 15 to 20 ppm, and very low delta D value, as low as -470 for the norite. And in fact, very low delta D values has been also inferred from the same sample in apatite by Jessica Brown in another study in 2014 at the Open University. And so now, if we suppose that there is degassing of the residual magma ocean, we're going to lose hydrogen, so we're going to increase the delta D in the meantime. And so the next source cumulate to crystallize from the lunar magma ocean are the one for the low titanium basalt, so 12004, 12008, 12020. And as you can see here, they are following this degassing trend with lower water content and higher delta D value. As we continue this crystallization and degassing, we are going to arrive at 70% of crystallization by the formation of the anorthositic crust sampled by the anorthosite 60015 here in red. As you can see, it is still on this degassing trend. However, as we reach this formation of the crust, this crust is going to act as a lead and prevent any further degassing from the remaining melt, which is below, because it's trapped and hydrogen cannot really escape this remaining melt, which means that the delta D value is going to stay the same for this remaining melt, but the water content is going to increase due to the incompatibility behavior of hydrogen. And so it means also that the sample from the crust should be the more degassed sample from the lunar collection. And it is also concordant with a study on plagioclase by Rui and co-authors in 2017. So next, we are crystallizing the ilmenite-rich layer, which is in part the source cumulate for the high titanium basalt. As you can see here, they have the same delta D as the crust with higher water content. So with this global scale degassing of hydrogen from the lunar magma ocean and the fractional crystallization, we are able to explain the huge heterogeneity in delta D and water content of the various lunar lithologies. And we are also able to infer an initial delta D at time 0, which is as low as -440 per mil. So this has a very big implication for the early Earth, mainly because if water was already present before the crystallization of the lunar magma ocean, it means that one of its formation bodies, so either the early Earth mostly and also maybe Theia, was also poor in deuterium. Because there is some studies that show there was no isotopic fractionation of hydrogen between the water from the early Earth and the water of the protomoon. Which also means that if the early Earth, maybe Theia, and also the protomoon were poor in deuterium, probably there was a pervasive reservoir of water, which was very poor in deuterium in the early solar system, because this value has also been estimated for Vesta, and also for the water ice that has been incorporated into a parent body of some chondrites. And so we suggest—
You have 2 minutes.
Thanks. We suggest with this study that the incorporation of the nebular hydrogen in protoplanetesimal at the early stage of the solar system was a very efficient processes. And so here are the conclusion of the study. Firstly, lunar reservoirs are very and highly heterogeneous in both water content and delta D values, which is why it's very difficult to infer an initial value for the moon. But we are able to say that this heterogeneity reflects a global scale degassing of the lunar magma ocean. And at the end, we suggest that the protomoon and the early Earth were very depleted in deuterium, suggesting incorporation of some nebular hydrogen in the early solar system history. Thank you.
That was great. Amazing. Well, I think we have time for maybe one question. We have about a minute.
Okay.
All right. Well, I have a question. I thought that was really interesting, and I'm curious about how we know what the deuterium ratio of Earth is now, the one that you're comparing to the moon, and how that sort of feeds into itself.
Well, we use the sample from the mantle, which is minus 60 per mil. But in fact, if you really look into the different reservoir of the Earth, there is some slightly variation. For example, the ocean have a different value than the atmosphere, than the mantle. And there is some studies that show that if you take that sample very deep, that mostly probably reflect the early Earth, it was also very poor in deuterium. So it's also difficult to infer a very precise value for the Earth, obviously.
Awesome. Thank you so much. So it is time for our next talk. We have our very own Kathy Met presenting on the origin of volatiles sampled by the L-Cross mission in Cabeus crater.
It's an honor to have the opportunity to share with you the research that we've been doing, re-looking at the measurements that were made by the L-Cross impactor. Now, to provide some context to this research, I want to talk about how we use the moon as a cornerstone for understanding the history of the solar system. And as part of SSERVI and part of the lunar community, I think most of the people online understand and recognize how we have done this, in particular with the impact history of the moon. We have the impacts on the moon that the record has been preserved for billions of years, thanks to the moon not having an atmosphere and liquid water and life. And that helps us to understand the history of impacts to the moon. And then there are other implications for studying the moon for our understanding of the terrestrial planets and for, in general, the history of the solar system. As the Artemis mission program is ramping up and the CLIPS program as well, we are facing an unprecedented opportunity to start using the volatiles on the moon as a cornerstone for understanding the history of volatiles in delivery to the Earth-Moon system and the history of volatiles on the moon itself. And the Viper mission is the very important first step in this process. Now, we have been studying water on the moon for an extended period of time. We've been using remote sensing to confirm that water is present on the moon and to try and map it. And we understand that its distribution spatially is patchy and with depth can be patchy, but we still have so much to learn just about water. In addition to water, other volatiles are really important for helping us to understand what the origin of this water is and where it came from. Now, the one measurement that we've been able to achieve is through the L-Cross mission, where they impacted the Cabeus PSR, which is one of the coldest permanently shaded regions. And we're able to measure in the plume from that impact molecules that bear carbon, nitrogen, and sulfur. And the abundance of these molecules relative to water and their composition is very important for us to try and trace back to the sources. But how do we go about doing that? How do we take this measurement and look at the sources that could have provided the water and these other volatiles to the permanently shaded region and figure out what the most likely source is or the most likely mix of sources? This can be very complicated. I'm showing on the left what the possible sources could be. They're volcanic, cometary, asteroid, meteorite, and solar wind. 3 of these are impactors. Understanding them from molecular composition is extremely difficult. When volatiles are delivered to the moon, they have molecular composition, but that molecular composition can change significantly because of all this mess of processes that take place between delivery from the source and then long-term storage in the permanently shaded region. So the best, and it's really difficult to figure out how many of these processes took place, what the rates were, how they impacted the molecular composition. In an attempt to get around this, what we have done is we've taken the molecular composition that was measured by L-Cross, both with the L-Cross mission and with the LAMP instrument on LRO, and looked at the elemental composition. So we're looking here at the carbon to sulfur ratio on the x-axis, or on the y-axis, and comparing that to the nitrogen to carbon, oxygen to carbon, and then carbon to hydrogen ratio. What we show in black is the L-cross observations, and there's two interpretations of the L-cross observations depending on how the ice was stored in the subsurface or in the regolith. Now, if these volatiles were stored in clathrates, which is water cages, what happens when the impact occurs is that the clathrates are destabilized and everything is just suddenly released into the plume. So we are interpreting the plume atmosphere as being, or the plume composition, if it's clathrates, as being representative of what's in the regolith. On the other hand, if the volatiles are just directly condensed onto the regolith grains, then their release is dependent on their volatility temperature. So some volatiles are released more easily than others, and because of the heating of the regolith, more of the more volatile species would end up in the plume than water. So for example, carbon monoxide is more volatile. So what appears in the plume is actually more than would be in the regolith. So we have these two interpretations. Now you can see from this figure that no single source perfectly matches the measurements that were made in the L-cross plume. So from this observation, or from this comparison here, you can't find a single source that without any fractionation of the element ratios would represent that. So what we have done is some modeling of what a mixture of sources of volatiles would be, what they would produce in the permanently shaded region and what would appear in the L-cross plume based on a mixture of sources. With this model, we have taken 4 primary sources: volcanic, cometary, chondritic, and solar wind sources, and then looked at 167,000 possible mixtures of those sources. And then we looked at 5 different scenarios, starting with assuming that what was stored represents what was in the source and no fractionation. And from that, we found that no mixture of volatiles actually fits either. We looked at volcanic atmospheric processes, and that, based on what has recently been published by Tucker et al., for example, well, some people have been studying volcanic atmospheric processes. This is extremely complex and difficult to constrain. We looked at impact loss to space and clathrate formation and sublimation and recondensation processes and how that would fractionate the element ratios. And what we found is that nitrogen and sulfur relative to carbon are really the key measurements for determining or ruling out potential sources for these volatiles. And the main conclusion that we found, because of the nitrogen to carbon ratio, is that it cannot be volcanic in origin. There's far too much nitrogen present in the volatiles to have a volcanic origin for the volatiles that were sampled by the L-cross plume. And this is after a rigorous, detailed modeling of hundreds of thousands of models that we have run. What we have found is that the best result is a mixture of cometary ices and chondrites. Now, comets are a mixture of ice, they're icy dust balls. And the refractory material in comets is probably chondritic in nature. So the observations that were made by L-cross could actually be explained by cometary sources because of a mixture of cometary ices and chondritic material. Now, in the future, as we start landing on the moon and studying these volatiles and making use of them for human exploration, it's very important to get in situ measurements, particularly of the D to H in water, and if possible, oxygen isotope ratios. We would also like nitrogen isotope ratios so that we can compare that with the known ratios of sources, and then sulfur isotope ratios are also very important. And with that, I will finish up. Is it time to move to the next speaker?
No, you're at exactly 8 minutes, in fact, so great job.
Okay.
Perfect timing. Yeah, so that
and
was...
we can make up time because we took up a little time with the introduction.
Yeah, well, let's see.
Know.
There any questions in the chat? No. I guess I'll ask a quick question. Clathrates on the moon. I haven't heard much about that. Any interesting things there to share?
Well, what we also found, because we took into account the way that clathrate formation would influence the elemental ratios, we found that clathrates are not a good explanation for the ices that were observed in the L-cross plume. So we did not demonstrate that clathrates exist on the moon. And I see in the chat, we have a question from Tom Orlando asking if we took into account the chemistry due to the impact. And we were able to kind of ignore that because we're not looking at molecular composition, and we're assuming that we don't lose elements in the impact. But we did look into chemistry and what that would mean. And I think the biggest implication of chemistry is that it would form N2 out of nitrogen that's present. And N2 was not observed in the plume because it is extremely difficult to observe remotely. And so the nitrogen to carbon ratio is actually, that was observed by L-cross, is actually a lower limit. And we did take that into account.
Okay. Well,
so I see
we
other
have a lot of
questions that I can answer in chat.
Yeah, I think we'll answer those in chat and move right along. And I'm going to attempt to actually use my timer this time. I think I'm ready to click fast. So next up, we have Paul Lucy talking about shy volatiles, how volatiles in the lunar polar cold traps may use physics to escape detection.
Okay, Elizabeth, do you hear me?
Yes, I do.
Okay, so let's see if I know how to advance my own slide. Okay, well, let's cut to the first slide here. So the basis of sort of everything I'm going to be saying for the next few minutes is centered around the fact that the stability of volatiles in the cold traps is exponentially dependent on temperature. So what you're seeing here on the left is from the classic Zhang and Page paper showing the sublimation rate of volatiles in units of meters per billion years versus temperature. You can see those curves are extremely steep. So the upshot of this is that there's a very narrow range of transition from where a volatile acts like a volatile, you know, it's chiefly in the vapor phase, or the volatile acts sort of like a rock. On the right is just a recast of what the Zhang and Page plot is. This is for water ice, and it shows the lifetime of 100 micron grain versus temperature. And you can see that in this range from about 100 to 110 K, the 100 micron grain can last the age of the solar system on the left to just a few 100,000 years or even much less on the right. So what I'm going to be showing you are temperature variations within the cold traps that span this critical range and can affect the detectability of volatiles by sensors that are coming up in the next few years. So let's see. Inability to advance slide. Okay, so the key parameter that have been used to map stability is our data from the Diviner radiometer. There's a lot of exposition here, but the short story is that Diviner provides temperature measurements in the cold traps at about 200 meter resolution. But within a Diviner pixel, the temperature lunar surface can vary substantially at all the scales about a centimeter. And the variation in the PSRs within those pixels is no different. So the temperatures that are used to produce the stability maps don't reflect precisely the actual temperatures that are experienced by the volatiles within those particular pixels. And the problem is really acute in PSRs that are undergoing indirect lighting, and when it's at its maximum, I mean, it's optimum for imaging. And I'll show that this may give rise to false negatives and will definitely dominate the uncertainty associated with what the volatile abundances are that we derive from the cold traps from these measurements. So how does subpixel temperature variation arrive? So the lunar surface is rough. And on the illuminated surface, this rough surface presents a range of incidence angles to the sun. This is a plot from J.P. Williams et al. The lunar surface is highly insulating, so the sun-facing slopes can achieve fairly high temperatures, whereas the slopes that are facing away from the sun maintain low temperatures, and shadows make this problem even worse. So what about the PSRs? So a PSR has a similar situation. Here's a picture of Shackleton, that illuminated wall that falls into the interior of Shackleton. The light falls on the sun-facing slopes of the roughness within the crater, not the sun-facing slopes, but the crater rim, illuminated crater rim facing slopes. And that gives rise to a wide range of temperatures within a diviner pixel that complicates predicting the stability. So what we've done is create a model. So this is an image of a computed fractal surface. We did two varieties of roughness, 6 and 23 degrees. So 20 degrees is the solution to diviner measurements of off nadir, which are dominated by this low, short range roughness. 6 degrees roughness occurs at somewhat larger scales. So we looked at these two cases. We illuminated the surface with a reasonable range of azimuth and elevations, so 90 degrees of azimuth and 1 degree range of elevation, computed the temperature from radiant of equilibrium, computed the diviner apparent temperature, what diviner would perceive, and then compared these to sublimation lifetimes. So we looked at two cases, quote, Shackleton-like crater, where the rim is about 20 degrees off the surface, and a Shoemaker-like crater, a large flat-floored crater, where the illumination is about 5 degrees off the surface. And here's a nadir view of Shackleton. So we looked at 90 degrees of azimuth and varied this azimuth to modulate the amount of lighting that the surface would get. So here's some results. So the little inset pictures is what the surface looks like in units of temperature for these cases. So this is the 20 degree elevation version, think of like Shackleton. The RMS roughness of 6 gives a very narrow range of temperatures around the apparent temperature. So this is the best case. But if we look at this, the RMS roughness of 23 degrees, there's a wide range of temperatures that go all the way down to a background, which in our model is dominated by heat flow. So this surface is starting to complicate the stability of volatiles in the surface. So with the 5 degree elevation angle, this is the Shoemaker case, and also diviner temperature of 100 K. The RMS 6 it shows a wide range of temperatures, bimodal distribution. And then the RMS 23, which again matches the diviner measurements on the illuminated surface, is strongly bimodal with a combination of relatively high temperatures and low temperatures present within the same pixel. So the problem starts to arrive is that while, I'll back up for a second, while this on the right, you can see a bimodal distribution. So let's call it a roughly 50-50 distribution of temperatures that are relatively high, near about 130, 140 degrees, and low, they have about the same area. The amount of signal you get from 3 microns, where you want to actually measure, let's say, water abundances, is weighted by the amount of signal that's available. So the
You're at
cold
8 minutes,
parts,
Paul.
thank you. The cold portions are biased towards low signal. So I'm just going to show this real quick. These are the different cases, but this is a cumulative plot, so that as you go from the 50-degree temperatures up to about 90, there's very little signal from those so-called icy surfaces. The signal is dominated by the surfaces that are illuminated and are warm and nominally dry. So this is a complicated plot, but the short story here is that most of the signal, in all cases, more than 75% of the signal, and sometimes more than 90% of the signal, is from the surfaces that are way too hot to preserve volatiles. This is the nadir case. Off-nadir viewing can either improve or exacerbate this problem. So the conclusions and implications: that the spectral measurements can underestimate the surface ice abundances. These are passive measurements, like were done by MCube and will be done by Trailblazer. I didn't go into it, but small amounts of surface ice can be present even where maximum binary temperatures are above 100 K. Off-nadir measurements can increase the apparent area of cold surfaces friendly to ice at the expense of total signal, but that total signal is mostly dry. And the abundance uncertainties that we are actually going to derive for ice are strongly tied to the estimate of the roughness. And I should point out that the laser reflectance measurements by lunar flashlight are immune to the bias from this issue and are uniquely suited to measure the effect of this off-nadir. Thank you.
Awesome. Thank you so much. That was really interesting. So I think we're just going to move right along here. If you have questions, definitely put them in the chat with Q in front of it, and we'll have discussion at the end as well. So next up, we have Carl Hibbets talking about a conundrum in the observed diurnal spectral variation of water on the moon, a spicy topic.
Thank you. Can you guys hear me? Hello?
Yes, I can hear you.
Okay, good. All right. Thanks for the introduction and thanks for the opportunity. I will be presenting a concept to resolve this conundrum in basically the kinetics and the flux of solar wind protons for the production of OH and its variation over a diurnal time scale. I want to acknowledge SSERVI as well as my co-author for contributing to this. So basically, a bit of a background: space weathering is affecting the surface of the moon because it's airless. A combination of solar wind protons, galactic cosmic rays, UV, micrometeoroids are all pummeling the surface. And as you can see in the image on the lower left from Noble et al., it produces a rind, maybe 100 nanometers thick, that contains amorphous materials, nanophase iron. And it's within this rind that the solar wind protons are implanted. And you can see this schematically in the lower right-hand corner, where the protons can form essentially OH. And this is a process theorized more than 50 years ago for the production of OH on the surface of the illuminated moon. And I want to point out that we're now transitioning to talking about the illuminated moon, not the PSRs. And we're talking about abundances of, tens to hundreds of thousand ppms, not percentages. So this theory was re-enlivened, I suppose, back in 2009 upon the discovery of a 3 micron absorption feature in the spacecraft observations of Cassini epoxy, as well as MCube on Shenzhen 1, with the example of epoxy shown in the space weathering schematic on the upper right. And if sufficiently warm, which means at non-polar latitudes, it's possible that thermal migration will occur with these protons, and that the OH can effectively migrate to form potentially H2 that can resolve as gas bubbles or migrate out as H2, or potentially even desorb as OH or H2O. But there are conundrums with this. I'm going to start with some other considerations we need to keep in mind. Is that the solar wind has very limited penetration depth. Only grains that are directly exposed to the protons will have implanted solar winds in them. That'd be the very top grain, possibly a grain or two beneath that, due to potentially saturations in the upper grain, which does take on the order of years to 100 years, could deflect the incoming protons to impact subsurface grains as well, maybe the top grain or one beneath that. And the OH then will desiccate from those grain rims that are not exposed or replenished from the solar wind over the time that it takes to absorb. Okay. Now this will result in two considerations. At the polar latitudes, shown on the lower left, it's very likely that the temperature is low enough that the migration will not occur, and that the grain rims will have OH on them, all of them will, and that due to micrometeoroid mixing, not really forming plumes, but mixing, that we'll have a well-mixed regolith of grains with OH on rinds throughout that. So we'll have a nice column of OH-rich grains on the rims. However, at non-polar latitudes, as I was just discussing, the OH will desorb from the rims and not being replenished by the solar wind. You only have a very superficial effect. Now we're getting into a potential conundrum and the solution to the conundrum. Conundrum being that the solar wind deposition and thermal desorption, the solar mechanisms are not consistent with observations or models. Solar wind implantation is simply too slow. But to explain the implied abundance variations that are large and rapid, it takes decades, as I mentioned, to saturate a grain surface with solar wind protons. And modeling suggests that only tens of ppms can be lost during a diurnal variation, which is an order of magnitude smaller than is suggested by the IR observations themselves. But I do want to say it would be consistent with the UV observation by Hendricks et al. The second conundrum is that OH loss is strongly temperature dependent, as I mentioned. Yet a diurnal variation is observed in telescopic observation at latitudes where the surface remains too cold for water to migrate. How can that be? It's going the wrong way. So let's go with observations relatively quickly. Here we're starting with MARE, Jessica Sunshine Epoxy data. We see low, shallow absorption band, noon, equator. In the morning, equator, because we're looking down at the South Pole, North Pole. So this is the equator. We're looking at the equator along here. This is noon, this is morning or evening. The band deepens. Similarly for highland material, equatorial highlands, shallow band, deeper bands, in this case, evenings. So this is dependent on time of day, but another way to look at it, it's also dependent on incidence angle, where the band depth is directly or is proportional to the incidence angle. When the sunlight becomes more grazing, the absorption band gets deeper, both for highland materials and for MARE material. And this is seen also in telescopic data as well. This is from Hannibal et al. 2020, showing that morning afternoon observations consistently show greater abundance. These are the chords, and this is some of the data that's been plotted. This is the equator, different latitudes. What I want to point out is that there is even a diurnal change. This is hours from local noon, so this is about noon. This is either morning or evening. That there's diurnal variation at poles. Is inconsistent with the physical motion of OH. Okay, and this trend is conserved when viewed in terms of incident angle. I took 0 degrees latitude here, the equator, because that's where we calculate incident angle for the sun without worry about alternator observations. So you can see that it generally has this kind of slope to it, consistent with early observations. Caveat, emission angles will not be negligible and can affect some of these interpretations, especially for telescopic observations. But talking about global distributions, we go this M-cube data. This is the typical one that we see. Overplotting the data from the work by Hannibal et al., actually symmetrizing it, converting it back and forth, it correlates more or less. The point is that both the latitudinal distribution and diurnal effects are consistent with effects due to or correlate with incidence angle. So how can we explain this? Well, I'll propose that these observed variations are primarily due to the effect of incidence angles coupled with the unique but largely stable distribution of OH in the grain rims. That if the OH is stable over longer than illumination, but not totally stable, then some will be lost, as has been modeled by Grant Jones et al. 2018. In the polar regions, none will be lost. And even though you have dominated by surface scattering, most of the light penetrating shallow and interacting with rims of grains along the surface and coming out. The changes some with the time of day, but always rather grazing will always have a deep IR band, getting deeper at more grazing angles, but always deep. Compared to non-polar morning or evening, still grazing, still have a relative deep, but not as deep IR band at the poles because one is sampling preferentially the OH-rich rims on grains at the surface. Compared to non-polar observations during midday times when the light is more vertical, the reflected illumination is from grains that have less OH in the rims due to volume scattering. And this is also consistent with UV observations. That even though UV observation or the UV absorption band, by the way, is 7 orders of magnitude stronger than the 3 micron feature, a very strong diurnal band is not seen, which is seemingly inconsistent unless one considers the fact that UV only penetrates the very first grain. It does not penetrate into the desiccated layer.
Carl.
Thank you very much.
2-minute warning.
Thank you. And thus, any diurnal variation on UV is going to be a real diurnal variation, a real loss of OH from the grain surface. The amount that is modeled by Hendricks et al. Is consistent with about 10 ppm bulk abundance variation, which has been modeled by Jones et al. So the UV observations are consistent with the models actually. And if you look at the diagram in slightly more detail, you can see the noon, midnight period, where at the equator, the absorption band can be deep, or the change is deep, whereas at the polar regions, the diurnal variation is almost nil, consistent with lack of mobility at cold temperatures. Caveats, it's not clear if the UV band is really indicative of OH, but most likely is because H2O is not going to be stable on the equator at all for detection. So these are the conclusions. We have 1 minute remaining. I'll just go over the recommendations that to resolve this or to truly determine if this is the case, we can do this potentially through remote sensing, through bidirectional reflection distribution measurements of the lunar surface in the 3 micron region, through orbital missions such as IceCube and trailblazers that can look off nadir. Also, landed measurements, taking care to avoid landing plume effects that can scour the surface, are another way to potentially check the hydration of the surface and even the near surface. And of course, you need optical constants for appropriate materials. So I'll leave this up and I'll end the talk now. Thank you.
Thank you, Carl. I think that's so timely and fascinating, and I'm excited to see where this goes. So we have about 20 seconds left, and there is one long question for you in the chat. So I'm thinking we may just go ahead and move on to the next speaker, and we can address that at the end. That's okay.
Hey, thank you.
All right. Great. So up next, we have Casey Hannibal talking about lunar hydration dependence on temperature from ground-based observations at 3 microns. Oh, Casey, we can't hear you. Uh-oh. Are we having technical difficulties?
Potentially.
Potential. Okay, at least we have your audio. That's a start.
Oh, you have it, my audio now?
Yes, yes.
Oh, okay, okay.
Proceed.
So let me try sharing my screen again. And you can see my screen and it's in.
Yes, you got it.
Okay, great. Okay, so hi everyone. My talk today is a perfect follow-on to Carl's, and it's going to talk about how hydration measured by the 3 micron band is dependent on temperature. So it's now been well established that hydration exists on the moon in the form of hydroxyl or water. It's most commonly studied through the 3 micron absorption band and has been measured by spacecraft and from ground-based telescopes. One important result from these remote sensing observations is that the hydration seems to be varying across the moon as a function of lunar time of day and latitude. The image on the left here is showing a map of hydration measured by the Moon Mineralogy Mapper on Chandrayaan-1 spacecraft. And on the right, we see estimates of abundance from hydration from the NASA Infrared Telescope Facility, or IRTF, located in Hawaii. Both of these observations are showing higher concentrations of hydration at higher latitudes. In the IRTF data, we can also see variations in hydration with the lunar time of day by looking at a constant latitude. This is harder to do with MCube, where the data was taken at only a handful of lunar times, while the IRTF is able to cover a wider range of lunar times of day ranging from 6 a.m. to 6 p.m. So with the IRTF, we are able to look at variations at the equator at times of day that are near the morning and evening, as well as noon. So by using wavelengths out to 4 microns, we are able, with the IRTF, we are able to strongly constrain thermal models. And what we found with the 3 micron hydration band is that it varies in a manner that is consistent with changes in abundance of hydration or hydrogen diffusing through the lunar surface, forming metastable hydroxyl. These observations with the IRTF provide confidence that the hydration or hydrogen is moving around the surface, migrating to colder temperatures at higher latitudes or towards the terminators. These plots are demonstrating the observed variations with the IRTF in 2 ways. The left is showing variations with latitude, while the right is showing variations with lunar time of day. Now, it sounds like the controlling factor for these variations of abundance might be the lunar time of day or latitude, but it's really temperature. So changes in hydration abundance with lunar time of day are created by the surface warming or cooling throughout the lunar day, and with latitude, the higher temperatures are at the equator and decrease with increasing latitude. So really the variations are due to changing temperatures. And so this top plot here is showing the higher hydration at high latitudes measured by MCube, and this correlates well with diviner temperatures shown on the bottom. So the goal of this project is to use the IRTF to understand the dependence of hydration on temperature. For this study, we are using chord profiles that extend from one pole to the next, like depicted by the red lines. We have collected 9 chords ranging from 6 a.m. to 6 p.m. with a temporal resolution of roughly 1.5 hours. We have looked at the morning chords and are beginning to process the afternoon ones. And for this presentation, I'm only going to show you one chord that was acquired at 9:30 a.m. lunar time. So these are going to be 2 videos that show normalized reflectance spectra with a line at 1. A 3 micron band can be seen when the data around the 3 microns is below the line. The first one here is showing a really nice deep 3 micron band. So now I'm going to start the video. So the red dot on the side of the plot here is going to show relative flux for each spectrum. When the temperatures are high, the red point will be high on the plot. The video on the right is showing the IRTF guider camera during the chord observation, showing where the data was actually acquired. So we started at the North Pole and are working our way south. And you'll notice that once the temperature increased, the 3 micron band is no longer present. But one important thing to note is that the 3 micron band didn't quite just disappear all of a sudden. It actually started strong and began to weaken as the temperatures increase and we move towards the equator. Once we start getting away from the equator and the temperatures start to decrease again, we'll see that the 3 micron band will begin to come back and will finally end on a nice strong 3 micron band. Now, if you're watching the guider images, you'll notice that the chord is actually covering all different types of terrains with shadows and sunlit areas. We have not yet begun to control for all of these differences and conditions, but plan to soon. And also we'll be taking into consideration the incidence angles that Carl was just talking about. So now if we plot the 3 micron band as a function of relative flux, we see that there are higher band depths at lower relative flux. Now, this is very preliminary work, and there are still a lot of things that need to be done with the data. First, we need to resolve the thermal model temperatures to align better with the diviner temperatures. We need to correct for negative values, which I believe are being created by the linear continuum that we use right now. Some negative values with a mean around 0 are expected due to scatter in the data, but the amount of negative values that we currently have and how negative they are needs to be addressed. And lastly, we need to fix the effects of saturation that are artificially masking 3 micron bands due to bad thermal model fitting. So like I said, this is all a work in progress, but we are beginning to look at this. But what we are seeing right now is a linear trend between hydration and temperature that are inversely proportional. This is actually different from what the hydration measurements in the UV see. So Hendricks et al. 2019 found a sharp decrease in the UV water ice band ratio at temperatures around 350 Kelvin, while we see a more steady decrease in hydration with increasing temperatures. The difference between the two could be due to the UV and the 3 micron band sensing different depths. The UV only senses the surface of grains, while the 3 micron senses the surface and interior. Also, the UV is 50 times more absorbing than the infrared. And so another possibility is that the UV hydration signal is so sensitive to the abundance and is so sensitive and the abundance is so high that the signal might actually be saturated at temperatures until the temperatures reach 350 Kelvin. The 3 micron band, however, is less sensitive and so may not actually be saturated and therefore is revealing the variation with temperature at higher abundances and lower temperatures. So we are also looking at how water observed at the 6 micron band varies with latitude but a constant temperature. Using the SOFIA Airborne Telescope, we have collected observations at 4 locations along the terminator, as depicted by these yellow points, plus 1 location at the north that is at a slightly higher temperature. The locations along the terminator should have roughly similar temperatures, and so we were looking to see if water is varying as a function of latitude independent of hydroxyl. We hope to have the data processed and in hand at the beginning of August, and hopefully many more observations with SOFIA to come to disentangle 6 micron water from the 3 micron hydration band. So that is all I had for today. Thank you.
Awesome. Thank you so much. So I think we're a little behind time despite our best efforts. So I think we're just going to keep going so that we have a lot of time for the discussion at the end, if that's okay. All right.
Can you hear me?
Yes, is that Abigail?
Yep.
Okay. Fabulous. We have you next.
Sorry.
Oh, no, it's okay. we're trying to trade off the intros right now.
Yeah, I was double muted.
Oh,
Hi,
my
Abigail.
goodness.
Welcome.
hi.
We would like to introduce to you Abigail Plum, who's going to be presenting telescopic hydration observations of Chang'e 5 landing site in partial eclipse.
All right, thank you. All right, so the detection of a global 3 micron feature, as we all know, indicates hydration due to hydroxyl or water. However, in order to look at that feature, you have to remove thermal emission contamination. And there is disagreement by experts as to how to remove this thermal contamination. For Moon Mineralogy Mapper data, there's at least 3 different methods for correction, and they provide conflicting predictions for the behavior of hydration on the lunar surface, as you can see in the plot on the right. So what we did to look at the Chang'e 5 site is I used the NASA Infrared Telescope facility to make observations between 1.6 and 4 microns, which goes out to longer, more thermally dominated wavelengths to help constrain this thermal correction. And we also exploited the changing temperature and illumination conditions before and during a partial eclipse. Partial eclipse is a helpful observation because the temperatures are reduced. The solar flux is also reduced, but by less than the thermal radiance is reduced. And therefore the thermal contamination at 3 microns is reduced. So we have observations from November 30th, 2020 UT, less than 24 hours before the Chang'e 5 landed on the moon. And so we have from throughout the partial eclipse, from 100% solar flux at about 365K to about 45% solar flux at around 300K. So for context, what we did is that red dot is the Chang'e 5 landing site, and we took we created a hyperspectral map using telescope data in that white box that you see outlined there. So when we look at the full illumination data, we do not see a decrease below the continuum around 3 microns, which indicates no hydration. However, when we look at our partial eclipse data set, we see a small decrease below the continuum, which could possibly be due to a hydration band. So we took a look at how this 3 micron band changes as you go to different illuminations. So as you can see at the higher illuminations, we see higher 3 micron band ratio, which would mean no or less water. And then as we go to lower percent illuminations or deeper into eclipse with lower temperatures, then we see a lower 3 micron band ratio, which would indicate more hydration. If we take this 45% illumination case and we translate the 3 micron band into ppms of hydration, then around the Chang'e site, you can see around 50 ppm hydration, and at various other points in the map, as much as 150 ppm hydration. So having no hydration band in the full illumination data set is consistent with predictions from other studies like Lee and Millikan 2017 and Honeyball et al. 2020. However, the possible hydration band that we're seeing in partial eclipse is unexpected. So, one possibility is that the hydration is changing during the eclipse. However, that would require either water to be migrating along temperature gradients, which is inconsistent with the upper exosphere limits by LADI, given the amount that we're seeing, or the temperature-dependent formation of metal-stable hydroxyl. However, we're in the magnetotail during eclipse, and we have been for days, so the timescale of hydrogen diffusion from solar wind is thought to be on the order of hours, not days, so that's a little strange. Then there's another possibility that we have to talk about, which goes back into correcting for thermal emission and how we're calculating reflectance. So the radiance that we measure is a combination of the reflectance times the photometric function and the solar radiance, plus the emissivity times the thermal emission model. And so if you assume Kirchhoff's law, which says that the reflectance plus the emissivity equals 1, then you can solve for reflectance, as you can see in that second bullet point, which is great, except when the denominator is 0. So if the solar radiance and the thermal radiance are equal, then you can't solve for reflectance. And so using this Kirchhoff's law assumption. And so this happened in our full illumination data set. So for the full illumination data, we had to use a thermal correction method that doesn't account for Kirchhoff's law. But if you have an emission feature and a reflectance feature being multiplied by the same radiance, then they can cancel each other out and it will look like 0. So at least for the full illumination data set, what's different might not be that the hydration has changed, but that our ability to measure it is different. And so this is a problem for that data set, and it's a problem for other places on the moon as well. And then as we go into the eclipse, the singularity isn't happening at 3 microns anymore, and we can see what's going on better. But, before we sort of dismiss some data as not having the information that we need, we kind of need to look at the assumptions we're making. So in the thermal infrared, beyond the wavelengths that we are looking at now, Kirchhoff's law is known to not apply. And it's unknown if it applies at 3 microns. So, that's an assumption that Banfield made, that's an assumption that Lee made, that's an assumption we were making. So that's something that really needs to be checked if it's causing problems like this. The other thing is that every pixel that we look at has subpixel roughness. So, each facet has a different singularity, wavelength, and temperature, etc. So it may be that by accounting for subpixel roughness, even if the singularity is in the way, we might be able to find a solution where we can recover some of the reflectance information. So in the future, we're going to be looking at Kirchhoff law's validity at 3 microns and addressing it. And in addition to that, for the Chang'e site, we have data collected from after the return launched, so we can compare that data to what was shown before landing as well, which will be really interesting. Thank you.
This is great. Thank you, Abigail. On the timer, we have 2 minutes left, but we are running late. So I think we're going to transition now to the lightning talks, which are 2 minutes each. And each of these 4 talks has a poster in the poster session. So you have plenty of opportunity to follow up with the authors as well during the poster session. We will give you a warning at 30 seconds. So the first lightning talk is going to be by Kari Fletcher, and it's on analysis of LADI measurements of H2 in the lunar exosphere. You have slides to share? There we go.
Yes,
Okay,
can you hear
can
me?
see your slide. Yes.
Awesome. Well, good morning to some, good evening to others. My name is Kari Fletcher. I'm a junior mechanical engineering major at the Howard University. I'm also a student data analyst at NASA Goddard Space Flight Center. As you can see from my title, my project basically focuses on analyzing the measurements of molecular hydrogen within the lunar exosphere from the Lunar Atmosphere and Dust Environment Explorer, which is LADI, launched in 2013. What's unique about this specific mission is that it's the first to take day versus nighttime readings of any molecular species within the lunar exosphere. And my project is the first to analyze molecular hydrogen in detail. From previous talks, you understand that understanding this specific molecule will give us a deeper understanding into the hydrogen cycle, the water cycle, as well as support the Artemis Sustainability Initiative for 2024. Our running hypothesis is that solar wind is the primary source of molecular hydrogen within the lunar exosphere. And our current understanding is that solar wind is implanted into the lunar regolith. Molecular hydrogen is formed within the lunar regolith, and then it is degassed into the exosphere. The current patterns that we're seeing from previous works is that solar wind increases during the new moon and decreases during full moon. And this has a lot to do with the moon's position in the Earth's
You're 30
magnetic
seconds.
field. Okay, thank you. So I highly encourage you to come out to my poster. As you can see, I'll be available tomorrow at 9:30 a.m. Pacific time at Station 12. I'll be going into more detail about our current findings, as well as into more detail about previous works and our current understandings. So thank you, and I hope to see you then.
Great, thank you, Kari. Our next speaker is Elizabeth Fisher, and she will be talking about identifying and characterizing surface absorbed water on the lunar surface.
Okay, this is going to take me a second here because I have the weird timer background set up, and I don't want that in my background while I'm presenting. Just a second here.
Yeah, I'll be keeping the time for you.
Thank you. Okay. Don't panic. Just keep clicking. Da-da. Okay. And then, thank you for your patience. It is very much appreciated. Share my screen here. All right, can you guys see a slide that is full screen?
Yes.
Okay, fabulous. So I am just gonna zoom through this really quickly. This is work that I've been doing trying to answer the question of whether or not we can use lunar spectra at 3 microns to try and discriminate between surface adsorbed and internally bound water in the lunar regolith. And I think that after all the talks today, it's quite a timely subject, because to be able to answer some of these questions that we have about, what exactly is causing the diurnal variations in the hydration signature that we see, it behooves us to know as much as possible about, the form of the water that is actually causing that signature. And the time scale of these variations implies that this water, it could be adsorbed, chemisorbed to grain surfaces, but it could also potentially be bound within grain interiors. So making that distinction would be fabulous. And the way that we're approaching this is we're starting by measuring lunar relevant materials in the lab. Here I have data for pelagic clays and tektite. And what we're doing is we're varying the amount of surface water on our samples by creating particle size separates, which changes the surface to volume ratio. Then we can use Hapke radiative transfer modeling to account for all of the effects other than absorption, and that leaves just the absorption signature of surface adsorbed water. And here I've just got a couple of examples of data where, you can see the 3 micron features for pelagic clays and glass, and you can see that the shape of this absorption is actually changing as you increase the amount of surface water. So those changes are indicating that there are, the surface and internal water have different bonding environments, and they look different in the 3 micron region. So perhaps we can detect that on the moon. And that's it. Thank you. Come to my poster.
Thank you, Elizabeth. All right.
It's tomorrow.
We will move on. We will move on to our next speaker, who is Christian Gescheidel. I hope I'm pronouncing your name correctly. Are you ready to share your screen?
Yeah, hi. I can't share it right now.
I am still sharing, sorry. I don't want to share anymore. Okay, there we go. Yep.
Okay. All right, thank you. So hello everyone, I'm Christian Gescheidel, a graduate student at the Technical University of Munich in Germany, and I'm glad to quickly present to you work on the Knudsen diffusion coefficient of order through NuLHT2M regolith stimulant. My colleague Laura and I performed at TUM in support of ESA's prospect study. Basically, we measured how the gas diffuses through regolith by measuring the transient response of a small gas pulse's flow through a sample. We used a high-speed pulse valve and a mass spectrometer under high vacuum, which is known as a fast pulse technique. To the measurements, we then fitted an analytic solution of Fick's second law and got the pore diffusion coefficients, which we then post-processed, gaining the desired diffusion coefficients of order through the sample. We varied the sample compactions and the sample temperatures to get a more broad view of the measurements. We found that for decreasing sample compactions and for increase in the temperature, the effective Knudsen diffusion coefficient also increases, and it to be in the order of 6 times 10 to the negative 6 meters per second squared. Our results are in good agreement with theory and literature, and they provide a basis for modeling volatile migration through regolith, for example, to investigate the volatile loss during sample transfer, in our case for the prospect study. So thank you for your interest, and especially for the great conference organization. We are happy to answer any questions you might have later. Our poster is number 12 at today's polar exploration poster session. Thank you.
Great. Thank you, Christian. So our last speaker is going to be Pedro Montalvo, and they will be speaking on contributions of impact mixing to the spatial distribution of water ice in permanently shaded lunar south polar craters Haworth, Shoemaker, and Faustini. Are you ready to share your screen, Pedro?
Yeah, I'm here. Let me. Okay, are you able to see that? Can you hear me? Oh, okay, perfect. Thank you.
And we can hear you.
Okay, thank you. Hello, everyone. I'm Pedro Montalvo, and I'm a PhD student from the Department of Geosciences at our university. And well, I'm happy to introduce to you all what my poster presentation is about. So with this work, we aim to analyze the spatial distribution of material mixing by impact cratering events in Haworth, Shoemaker, and Faustini which are located around the lunar South Pole, and give insights about water ice deposit concentrations. So this information is very valuable, right? Because for future lunar exploration missions that will sample and use water as a resource. So in this work, we performed crater counting statistics in these permanently traded floors and applied a statistical approach to model at what depth the regolith is being mixed by impacts. So we also calculated water ice fractions using parameters such as the density of water ice, the depth of an initial water ice layer, and the density of regolith, and our model mixing depths. And we also updated our model results from our presentation from last. And here we provide new insights towards the distribution of water ice that is being mixed at depth throughout these permanently traded floors by using a gridded approach at different scales or sizes. So if you want to hear more about this and want to discuss more about this project, please join me today at 10 a.m. Pacific time, which is about 12 p.m. Central Time where I'm at, during the poster session 2, Planetary Exploration, at poster number 11. And with that, thank you for your time.
Great, thank you, Pedro. So now we are going to move on to the discussion time where we can take questions and have discussion on each of the 10 presentations that were given. There have been some questions that have been put in the chat and have been answered by the speakers already. Do we have any new questions that anybody would like to pose for our speakers?
Yeah, so I think if you had a question in the chat that was earlier and you didn't get it answered at that time, just throw it in there again so that we can see it. And also feel free to raise your hand and ask the question in person.
Great, so I see Shuai Li has his hand raised.
Yeah. I have a question for Carl. So like, have you considered like if we use like a radiated trans model, like a Hapkin model, to convert like those reflectance to single scattering albedo and then calculate the band depth? Will that help to reduce or remove the effects of ring geometry? Like you're thinking, you know,
you would be more the expert.
Well, I think I can.
Yeah, so you'd be more the expert at that than I would be, Shuai. I think what approach we're taking is simply to use models from, how's it, Bohr and Huffman. I can't remember which text we're using. Dave Blewett has found some models he can use to calculate the Hapkin reflectance based off of coated spheres. And so it's going to be actually 2 models of a coated sphere underlain by basically plain old spheres that don't have any OH in them. So that's the approach we're taking. I'm not sure if it makes sense to use an SPAT approach, if that's what you're talking about, to derive abundance, if we're basing that on a model that does not assume coated spheres. But again, I'm relying on the model expert, Dave Blewett, to do that for me, and your insights would be great as well.
Okay. Yeah, well, I think what I've done is just intermittent mixing. Yeah, I think trying to use like a different layer and I see how it goes. Yeah, that's a good point.
Okay.
All right. I see another question in the chat from Kevin Dupriest to everyone. That is the lunar atmosphere pressure being considered? The pressure of this small mass is around 310 to the negative 15 ATM, varying throughout the day, and in total mass less than 10 metric tons. Is that enough to affect these results? So basically, is the exosphere being considered in these measurements that everybody's been making of the 3 micron region, which I think is an interesting point. Any takers? I mean, as a spectroscopist and the uncertainties associated with the spectroscopy, I mean, I can take a stab at this. I think that the exosphere is just, you know, it's such a low concentration of molecules. You know, spectroscopically, when you're looking at lunar, you know, at least reflected spectra, there is already an inherent degree of uncertainty in those spectra from the spacecraft, the surface roughness, et cetera, et cetera, et cetera. And I don't know, this is just my educated guess, because I don't really do a lot of exosphere stuff, but I think that the influence from the exosphere to a spectra in that context would just be so tiny that it would be overwhelmed by the already existing uncertainty associated with the measurement. And people, feel free to jump in if you have thoughts on that.
I see a comment from Paul Lucy in the chat. Do you want to speak to your comment, Paul?
Oh, I was just referring to a couple comments before about the band depths, but Yuri Skiratov and Ludmila Starkina showed that just from doing modeling, you get stronger band depths in brighter material, i.e. highlands. So we need to throw in composition as and space weathering as a modulator on the 3 micron band above.
Yeah, absolutely. Yeah, I think that, you know, considering the effect of composition on all these measurements is, I mean, I'm biased towards my own research, but I think that is a very important next step, because I can already see in my studies of like the specifics of the 3 micron region, the way the shape and intensity of that feature looks and changes is very different on the basis of what mineral or material you're looking at, because they all have, you know, different structures. You end up with different bonding environments. So yeah, I think that's an important point to make.
Absolutely. Darby Dyer would agree with that. She has demonstrated, she makes measurements that has in the past, along with her previous advisor, I forget the fellow's name, in the mid-80s, published on the different absorption strengths for water and different minerals. There's definitely an effect. It's not a factor of 5 or 6, but you know, it's an effect that needs to be considered. Also, the position of the band changes significantly. So the identification of water by the position of H2O by the position of the 3 micron band may not be accurate if you're looking at anorthite material, which tends to have a OH feature that shows at longer wavelengths than in more mafic minerals.
Yeah, exactly.
I have a question for the presentation of water looking during eclipse. Was potential effect of absorption by water in the Earth's atmosphere of sunlight, you know, during the lunar eclipse considered? The light from the sun, I believe, be passing through the Earth's atmosphere that contains water. Could that have induced a 3 micron band in the apparent reflection spectrum from the moon's surface? That was Jessica, I think, who presented, if I remember the name.
That was Abby, but
Abby,
I'm not
sorry.
sure if she's around still, so I can try and address that a little bit because we, you know, work on the same data. When we observe on the IRTF, we take spectra of a solar analog star to hopefully remove some of the atmospheric water in the band. But under eclipse, the observing conditions are quite a bit different. But in theory, we are attempting to remove almost all the atmospheric absorptions as much as we possibly can. So we are seeing mostly the water that's on the surface. And also the atmospheric water is in more of a gaseous phase versus like on a solid surface. So I'm not sure what that would look like in our 3 micron band in our IRTF observations. I think that would look very different for us. Maybe Paul has something to say on that if he wants to jump in too.
Yeah, I think what Carl's saying is the light from the Earth reflected off the lunar surface not
Yeah.
the atmospheric effect. So, Carl, we've measured the reflectance of the moon during total eclipse, and it's almost 100 times fainter than the reflected signal we get from the direct illumination, even during partial eclipse. So, we haven't actually corrected for it, but it's going to be small, and it doesn't show a real obvious water band. We're actually kind of disappointed in that.
I bet. I was actually thinking of the light in the penumbra, whatever, that would contain some sunlight that was absorbed by water in the atmosphere before it actually reflects off the surface of the moon.
Oh, like an exoplanet atmosphere.
Yes, exactly.
Yeah, you do see this in total eclipse, and you see beautiful atmospheric features short of 2.5 microns. For whatever reason, it's flat as a pancake in the 3 micron region.
Interesting. Yeah. Thank you.
All right. I think that we've got a good comment in the chat, and then I'm considering posing a question to the group. So Tom Orlando has pointed out that some folks mentioned OH migration. I want to point out that this happens via proton hopping, and the center of mass of O is not moving. The relative concentrations of OH at the surface ends up changing. The survival of these are very temperature dependent. They end up making some water that can leave. I think that's a really good point. And Tom, correct me if I'm wrong, but didn't you and was it, oh my goodness, how am I forgetting her name? My brain is fried. Didn't you have a paper that you were a co-author on that particular subject relatively recently?
Brant Jones is the primary author on this. We had a couple of papers on this, and then we also related it to Mercury.
Okay.
Yes, actually, and if Brant is tied in, he could comment on this. It turns out if you apply this model, it maps out exactly what Casey was showing in terms of the latitude and temperature dependence of the 3 micron band. Their data is very well reproduced by the model. Brant is actually the primary modeler. And if he's on, he could chime in, but he's the person to talk to for the modeling.
Mm-hmm.
Let me jump in though. The magnitude of the change that we were on, I was on that paper too, was small compared to the magnitude of the change inferred from the variation in the IR band. So while the distribution is very well matched, the magnitude is not by as much as an order of magnitude. And
that's with regard to that's with regard to the magnitude changes from Shawlee's paper and MCube data. But if you look at some of the slope changes and things that Casey was showing, I think it matches better.
Yeah,
it did match the 0.1% monolayer thickness from the Hendricks paper.
Yes, exactly. That I presented that.
Yeah.
Matches UV stuff well. Doesn't account for the larger IR difference. And I just want to point out, in Micah's paper, he references 2014 paper with Gradiola. It looks like that absorption band for that it takes equivalent of over 3 years of proton irradiation to create that size absorption band if that were on the moon. And we want to bring this up that we need to consider fluence and flux as well as total abundances and things of that nature. And I think we have a fundamental issue in terms of the solar wind not being a high enough flux to account for a diurnal radiation. I won't rehash my presentation.
Okay. Thank you, Carl. We have another question in the chat, and then we also have a hand that's raised. So I'm going to first go with Parvati's question to Alice. Do you have thoughts on what sort of measurements or samples would help in further understanding the contribution of nebular hydrogen to the Earth-Moon system? It seems like that might be the oldest flavor of lunar volatiles. So I'll hand that over to Alice.
Yes, sorry. Yes, so I think the sample we are trying to look for is the one that are supposed to be the most primitive into the lunar mantle. So the one that are mostly island materials like the norite, because at the end we have one sample that has the lowest delta D value, from which is at the bottom of the degassing trend, but we need a bit more sample to make sure this value is really recorded in other samples too. I don't know if that makes sense. So.
That was an excellent question, and thank you, Alice. So, OJ, I see you have your hand up.
Yeah, this is more so of a comment. I just sort of like to advertise a paper we did in 2018 where we looked at the diffusion of hydrogen using an activation, a distribution of activation energies. And, we were able to obtain a good agreement in abundance and the latitudinal dependence consistent with Shiley's results. So, please take a look at that paper too. And we also have a more recent one looking at how it changes when in the magnetotail, 2021.
That sounds fabulous. If you could link those in the chat, that would be great so that people can grab the citation and take a look at those. All right, well, I want to pose a little group thinking exercise to the group, since I don't see any hands up, or I think that OJ, you have a what was it called? Somebody had a funny turn of phrase for this. You have like an old hand up. But I'm wondering if any, like, we've just talked about a lot of potential influences on this lunar hydrogen cycle that we're observing, surface roughness, temperature, sun angle, et cetera, et cetera, et cetera. If you had to sort of pick one arena that you think would be the most important to move forward in terms of better understanding the lunar hydrogen cycle, I guess, what do you think it would be and why? And if we want to take 30 seconds or a minute and have people post their answer in the chat, I think that could be fun. Kathy, I don't know what you think.
Yeah, I like that idea.
Okay, yeah.
It'd be interesting to see what people come up with.
What's your takeaway here?
Yeah. So while we're waiting for people to put questions in or to put their thoughts in the chat, I have a question for Pedro. Have you considered any work of doing comparisons of your research with the maps and the data from LRO that is available? Pedro's still on.
Here's Pedro is not still on.
We have lost Pedro. Okay,
Oh,
I will have to visit.
Okay.
Oh, wait.
Poster.
Kathy.
Okay.
Is that?
Yeah. Oh,
Yeah, this is Toshi. Yeah, I'm working with him.
Okay.
So yeah, I'm working with him. Regarding your question, that's a good point. We are currently working on that. Definitely. So the major part of his work is like trying to understand the mixing depth and the correlation with ice content concentration rate. Definitely like using data, and especially LRO would be very important. So yeah, he's currently working on that. Thank you for your question.
That's great, and I would welcome him to get in touch with team members from LRO, because we'd be very happy to help him with understanding any of the data products that we have. We love
Sounds
having
good.
everybody use our data.
That's great. Thank you.
now have a stream of comments coming in. And
A+ on
see
class
Elizabeth.
participation, guys.
Yeah, yes. I see Elizabeth frantically making notes.
It's usually worth 10% of the grade.
Yeah. But I mean, what's the saying that, you know, 50% of the effort when you're doing something is just showing up. So I know I'll count it higher, and you know, I'll weight it higher for the overall grade I will give this this group. Okay.
Yeah. Very
So
good comment.
you just want let's start taking a look at some of these. What do you think, Kathy? Should I just read them?
Yeah, that sounds good. So it starts with Paul.
Yeah. All right. So Paul started us off with laser reflectance at 3 microns, global night and day. And I personally am very biased towards that, of course, because I did laser reflectance and had a rollicking good time looking in the PSRs. So, and yeah, if people have comments or thoughts on this, yeah, just throw your hand up and we can discuss more. Casey Seconds laser reflectance. Oh, Jeff asked me to put the question in the chat and I didn't. I'm very sorry. Jeff, if you're still here, I hope you were able to participate despite me not seeing that comment. All right. Carl has more observations, especially bidirectional reflectance of the lunar surface from orbit and ground, including microscopic imaging at 3 microns. That's fun. Of just like soil or regolith grains, Carl, you know, just doing.
Yes. Of the regolith, both disturbed and undisturbed. Because from landed, if you look at the disturbed soil, you might actually see what pristine soil looks like, or even look at the hopping of water across that from the plume material. It could be your own experiment for, you know, water absorption, desorption from a landed experiment.
Oh, for like a lander.
For a lander, yeah, right. That could be really interesting about understanding the migration of H2O or adsorption as OH. But from orbit, I'd really like to resolve this whole idea we have of incidence angle dependency. But I like the laser stuff, especially with PSRs. How else are you going to measure it in PSRs without active illumination?
Yeah,
yeah,
absolutely.
There is a problem with the photometry at 3 microns, is that it's still a mixed reflected thermal emission signal. So you can't do like we do at shorter wavelengths. You need to solve that problem before you can solve that problem.
Yep, and Abigail Flom actually said that as well, as like what she thought the most important thing would be for moving forward here. I think that's a great point.
Yeah, that's also partially because Paul and I are going to do some lab experiments to take a look into that problem. So.
Oh, so you're coordinating.
It's on the mind.
Gotcha. Yeah. Well, I can tell you, I agree strongly.
Yeah.
For the 3 micron measurements in illuminated terrain, because the water is relatively stable, as long as you have a good thermal correction, then you should be able to accurately measure the shape of the band. It should not be dependent on the temperature of the grains, because those grains are going to see all the various temperatures at some time of day. So you should be able to see some average band. It's not like in the PSR where if you look at it, you know, it's very different.
Absolutely. I do think, though, I'll make a short comment on the photometry, as from the perspective of someone who's been trying to do radiative transfer modeling in this region. I can barely get away with it because we're at Earth-like temperatures in the lab. If you heat that up at all, you start having, you know, thermal influence, but the assumptions that you're making about the physics of how light is interacting with particles in that region also begins to change. You start getting into this crossover region, which in terms of like understanding like the actual radiative transfer processes and like how it's playing out in there, it's still kind of the Wild West. My office mate, Chris Kramer, works on it, and we have a lot of discussions about what the heck might be going on.
You have emission, emissivity, you have to separate temperature, emissivity separation is a big
yeah. So from a modeling perspective, that region is still kind of a nightmare. So yeah, I think that's a great point. So we have from Laszlo that nitrogen is important to measure, but photometry is a pain and you can't ignore it. Oh, yep, Laszlo also agrees. I think we're sensing a trend here. OJ Tucker has temporal variation of hydrogen in the exosphere to constrain chemical formation rates in the regolith. And yeah, I don't know if anyone can speak more to that, who knows more about exospheres.
Yeah, we had the Laddie presentation on each. That was by Case or Kari. Is Kari still on?
Everybody left.
I think Laddie is the best bet for measuring H2 because of in situ. With LAMP, we measure the exosphere, but I'm not too sure how many H2 measurements we've got.
Right. I mean, LAMP. Right. So, so far, LAMP hasn't been able to extract like the diurnal variation. They looked at the morning and evening terminators, and Chase did like a short measurement while in the magnetotail. So really, all we have is Laddie right now of H2, and as Kari talked about, it's really difficult to sort of extract the H2 densities from Laddie because just so much noise. So, but I think, in the future, if we can, really get an idea of how it varies temporarily, then we can understand better the solar wind contribution to H2, forming H2 and other hydrogenated species in the regolith to sort of help constrain some of these ideas.
So the current state is that it's really hard to measure and we don't have enough information, basically. Yep. Ari, do you have anything you'd like to add? I see that you're still on.
Perhaps.
You are muted. Yeah. Okay.
All right. I just realized that in my excitement to say that a lot of people agreed with the photometry point, like how that's a pain and we really need to figure that out before we proceed, I skipped over Schwei. I'm sorry, Schwei. Schwei said that regarding the fact that most OH H2O could be concentrated in grain rims in the top tens of nanometers, diffusion of H could be significant at relatively high temperatures, such as above 350 Kelvin. Yeah. Schwei, do you want to expand at all, or?
Yeah, so this is like what I got from OJ and also from Bill's work about the diffusion. And also I did something like modeling work. I feel like because as we know, the solar wind implementation only occurs like on the top, like maybe up to 20 to 50 nanometer on the surface. And at least has been demonstrated with Apollo samples. So like that's a so thin layer, right? Nanometer, 10th nanometer. So I'm thinking like a hydrogen can be very mobile at like a relatively high temperature. It can just move around. Because once the hydrogen moves away from oxygen, you won't see any OH feature. So that means like, as the temperature changes, like the H moves around, and also you will observe the OH feature change.
Yeah. Yeah.
Yeah. So I saw Tom also had a comments on it. So I'm not sure Tom wants to explain more about what his thoughts.
Yeah, and I'd just like to mention really quick that further down in the chat, great minds think alike. Pavarthi also was talking about how she'd be really interested in understanding the physical form of H on the surface, how much is migrating, locked up in rocks, etc. Agnostic on method. But yeah, I think that this kind of speaks to a larger trend that I've noticed, that it's like we tend to get stuck talking about water, but it's been really helpful for myself to reframe this as like we're looking at a hydrogen cycle, like, and taking a step back and thinking about how hydrogen is behaving in the environment and how sometimes that might result in hydroxyl in water and sometimes it might not. and considering.
So we have
Yeah.
reached the point of transition to plenary, and I think our
Okay.
panel is the one that is used for the plenary.
Okay. Yeah.
So
I
this
thought
has
we
been
had.
a great
Oh, we're at the end.
discussion. Yes.
Oh dear. I'm
It's
sorry. I
going
feel bad
very
that I was
quickly.
talking.
That's okay.
Yikes.
So
I thought
we
we had
want
more
to
time.
thank everyone who participated in this session. It was really great presentations and wonderful discussion afterwards. And I think we've got a 5-minute transition now to the plenary that's coming up on the PRISM Payload Suites panel. So want to thank everybody for coming.
Yeah.
And thank you, Elizabeth. Do you have anything, last words?
I hope it was
You've done an amazing job. Yes.
Yeah, but this was really fun, guys. Thanks so much, and thanks for participating. I hope you guys had a good time as well.
All right. Bye, everyone.
See you, everyone.
Thank you, guys.
Welcome everybody joining from the other morning session. The plenary session will begin in about 5 minutes.
Ricky, this is a sound check.
Brian, your audio and video look good and sound good.
Thank you.
Hey, how's my sound?
Sounds good.
Hi, Brian. Hi, Ricky. Sound check.
Sound good. Staying dry?
Trying my best.
Did I put up my first slide to make sure screen sharing is working all right?
Sounds like a great idea.
And we're just about a minute away from our scheduled start time. David, that's looking great.
Okay, good, thanks.
There's a whole lot of Reiner Gamma there.
Yep.
And then David, the only other thing would be your camera when you're presenting. Oh, perfect. Yeah, looks good. We've reached the official start time for this session, so I will leave it up to you to begin when you want. Also, would you like me to provide the 15-minute timer for each presenter?
I think that'd be fine, but I think we'll probably give them a little bit of latitude and push into the discussion if they do go a little bit over.
Okay, I will leave it up to you guys to manage that. Thanks.
Okay, thank you. All right, so at this point we'll begin. Welcome to the PRISM Payload Suites panel. I'm Brian Day from NASA SSERVI, and I'm joined by my co-chair Valentin Bickel from the Max Planck Institute for Solar System Research and the Swiss Federal Institute of Technology in Zurich. The Payloads and Research Investigations of the Surface of the Moon, or PRISM program element, solicits proposals for investigations that include development and flight of science-driven suites of instruments and technology demonstration payloads that will be delivered to the lunar surface through the Commercial Lunar Payload Services, or CLPS program. We were all excited to see the announcement of last month of the selection of the first 3 PRISM payload suites. Valentin.
Oh, thanks, Brian. Today we'll hear about details about these suits from David Blewett, who leads the Lunar Vertex Joint Land and Rover Payload suit, headed to Rainer Gamma. We'll hear from Mark Panning, who leads the Farsight Seismic suit going to the Schrödinger Basin. And we'll hear from Robert Grimm, leading the Lunar Interior Temperature and Materials suit, also designed for Schrödinger. Each panelist will get 15 minutes to present. A friendly reminder, please enter your questions into the chat to be answered during the session and discussion after the presentations. All right, David Blewett from APL is first up with Lunar Vertex. Stage is all yours, David.
Okay, good. Thanks. Fun to be here to talk about a magnetic anomaly. Okay, I guess I have to click to advance. Right. So, lunar magnetic anomalies are really interesting from a number of perspectives. The moon lacks a global magnetic field, but there are local patches of magnetized crust. The origin of these magnetic anomalies is unknown, and there are several hypotheses for their formation. These fields modify the moon's interaction with the solar wind from what it would be if the moon was just a dielectric sphere. Observations from a number of spacecraft have shown that standoff regions or mini magnetospheres exist over the stronger anomalies. Modeling has also provided insight. There's an example shown there on the right. But the flux and energy of the ions and electrons that actually reach the surface are unknown. Then there's the matter of the lunar swirls. Most magnetic anomalies are co-located with unusual albedo features called lunar swirls. The type example is Rainer Gamma there in Oceanus Procellarum. The origin of the swirls is unknown, and there are several hypotheses for where they came from. So I think the magnetic anomalies really represent superb natural laboratories. They're a place where we can go to examine sets of key questions in several different areas of planetary science. I see these as really compelling problems that bring together what Don Wilhelms in his book To a Rocky Moon called sky science, right? Particles and fields. They bring that together with geoscience. And one in particular, when it comes to space weathering, it's likely that the surface within a magnetic anomaly experiences an atypical space weathering environment. It's thought that the 2 prime agents of space weathering are solar wind exposure and micrometeoroid bombardment, but the shielding effect of the magnetic field should attenuate the solar wind to some degree, but it won't affect the micrometeoroids. So we've really got a great control experiment on understanding these 2 key variables. So, among the unique opportunities that are presented here, we can look at problems in planetary science, including geophysics. What is the nature and origin of the magnetized crust? Does it involve an ancient dynamo and remnant magnetism recorded in intrusive or extrusive rocks? Or could these magnetic anomalies be related to field amplification effects associated with plasmas, associated with basin forming or comet impacts? There's the space plasma physics angle, the formation of the mini magnetospheres, the flux of these species that make it down to the surface, and how do these all change with time of day? And of course, the geology and surface processes. I mentioned the space weathering, the solar wind versus the micrometeoroids, which may be involved in the origin of the swirls, but there are other hypotheses, including unusual motions of levitated dust or interactions with dust and gas in the coma of a comet. And also there's the potential for unsampled rock types with unusually high metallic iron contents, depending on what we determine the actual inherent magnetization of the magnetic source to be. So my colleagues and I have been promoting a magnetic anomaly as a mission target for quite a number of years. Fortunately, apparently NASA was persuaded because last year, the target for the PRISM 1A mission delivery was announced to be Reiner Gamma. So at APL, we responded to that announcement by writing a proposal, the cover of which is shown there. And the goals of our mission were to investigate the origin of magnetic anomalies, determine the structure of the mini magnetosphere over Reiner Gamma, the Reiner Gamma magnetic anomaly, address the origin of swirls, and then in the process of doing those first three things, you kind of end up doing the last two. One of which is, again, evaluating the relative importance of the two perceived chief agents of space weathering. And we can also provide some data related to certain strategic knowledge gaps, SKGs, for human exploration. In order to accomplish those science goals, we have a set of instruments on the lander. There are three on the lander. The first is an array of fixed cameras that provide a 360-degree panorama view of the landing site to help understand the context and geology. And those data will also be used for photometric modeling. There's a magnetometer. We're going to a magnetic anomaly after all. So we have a primary ring core flux gate that's on a mast. And with it, there are 4 inboard magnetometers that serve to sense the lander field. Now, importantly, the magnetometer will make measurements during descent as well as afterwards on the surface. That descent profile of the magnetic field strength and direction is really key for helping to constrain the nature of the magnetic source. And we have a solar wind spectrometer to measure ions and electrons in the plasma energy range that are incident on the surface of the moon. We also have a small rover that will deploy from the lander. It will carry 2 instruments. It will have another magnetometer that is a copy of part of the lander mag. This will allow us to determine the spatial variability of the magnetic field. And we have a close-up imager or multispectral microscope that will provide data on the composition and texture of the regolith beneath the rover during science stops. So, for this, it's really important to get away from the area messed up by the lander rocket exhaust so that we can examine pristine areas away from the lander. Although it will be very interesting to examine and compare the lander disturbed regions with areas farther away, kind of at the microscopic level, for comparison with the sorts of changes that are observed around landing sites that are observed from orbit. Our landing site will be somewhere near the edge of the large central bright swirl region at Reiner Gamma. This will give the rover the chance to make a traverse toward, into, and hopefully across the so-called dark lane that is adjacent. We're still in the process of examining potential landing sites and traverse routes, but we think we can drive at least half a kilometer and maybe as much as 1 to 2 kilometers. This shows the science team. The deputy PI is Jasper Halikas. Some of the names on here may be somewhat less familiar to this lunar audience because they are members of APL's heliophysics and space physics group, but they've got great credentials when it comes to instrumentation, magnetometers, charged particle detectors, as well as the science thereof. So we think we have a really good team, a good mix of late, mid, and early career people. Just something about the mission's name. In Latin, the word vertex can mean swirl or whirlpool or vortex. But in English, a vertex is an intersection. So we see our mission as representing the crossroads of geoscience and the particles and fields domain of space physics. So we've got an interdisciplinary mission, and this intersection is our theme. Just to conclude, Lunar Vertex is a PRISM mission to the unique environment of a lunar magnetic anomaly, and we're going to be addressing key decadal and scientific context for exploration of the moon questions in major subdisciplines of planetary science. So I'll stop there. Thanks.
Awesome. Thank you very much, David. Mark, you can start sharing the screen. David, if you could stop sharing, that would be great. So Mark, you can take over.
Okay, I'm working on that. One moment.
Take your time.
Okay, is that visible to people?
We are now in.
Okay, how's this? How's that? That better?
That's perfect. Thanks. All right.
It always wants to figure out whether it wants to do the presenter tools or not.
Are you good to go?
Yep, I can go ahead and get started. A couple minutes early, so.
Briefly introduce you, Mark. So next up, we have Mark Panning from JPL with the Farsight seismic suit. All right.
Hi, everyone. Thanks for the invite. It's great to talk to a group like this. So this is the full list of authors, which is really just the proposal team right here. So you can see on the list here, there's a lot of seismologists on this list. And also some great technical people that are going to be delivering this instrument suite to Schrödinger crater on the far side of the moon in the PRISM 1B mission. Let's see here. Okay, so this is kind of the whole talk in one slide. So I'm not going to talk about everything on here, but when you go back to the recording and look and see what's there, you can see the whole story in one slide if you're interested in. And so what we're doing with Farsight Seismic Suite is we're delivering a couple seismometers, a vertical component, very broadband seismometer, which is the most sensitive seismometer to fly on a planetary mission, and also a capable compact 3-component short period seismometer. And these are both based on instrumentation of the InSight mission, which is operating on Mars right now. In fact, the VBB is actually using a flight spare from the InSight mission. And we're putting all of these inside a thermal enclosure that has its own independent command, power, and communication system. So effectively, we're a CubeSat without propulsion. And the idea is that we outlive the commercial lander, continue operating through the night and recording data, communicate during the day, and last for a nominal mission of 4 months in order to record the moonquakes we want to see. And we're aiming at 3 primary science goals in this process. We're trying to look at the far side seismicity, which has never been analyzed because all the Apollo data comes from the near side, and look at implications thereof. We're also looking at the local crustal structure underneath Schrödinger crater and linking that into global crustal models. And finally, by putting such a sensitive instrument out there, we can record the background seismic noise better than has been possible in the past, which can be linked to micrometeorite impact rates. So those are the 3 main science goals. So, now that you know the whole story in advance, let's step back and think about how we do seismology on the moon. It's very different than Earth seismology in a lot of ways. So on over here on the left, I've got 2 seismograms that are both 1 hour long. One is from Earth, one is from the moon. Same time scale, similar sized events. And you can see that the moon is very, very different than the Earth. So on the Earth, we get nice, clean arrivals that give us this nice spike here showing up. On the moon, the scattering, the seismic scattering is intense, and everything oscillates for long periods of time, an hour or hours. And this adds a lot of complication to how you do seismology on the moon. The Apollo measurements, of course, were only made at near side landing locations. So by taking these modern sensitive instruments on the far side of the moon and adding in modern digitization, I mentioned digitization here because I show a recording of a small moonquake here at the bottom, which shows the limits of the I believe 7-bit digitization used by the Apollo instruments, where a lot of small moonquakes look more like barcodes than seismograms. And this was a fundamental limitation of what could be done for the small events in the background noise for Apollo instrumentation. So we're really getting a chance to explore a lot of new ground here in this far side mission. Just in a little more detail here, this is plotting the major seismicity locations as recorded by the Apollo stations during the 70s. And all of these circles here are locations of deep moonquakes. These happen hundreds of kilometers deep, and they tend to happen in repeating clusters. So they happen over and over again at repeatable times in the tidal cycle. And then the blue stars are shallow moonquakes, which are the larger quakes that happen once every several months or so. And you can see the orange box is highlighting the near side of the moon. Basically, all of the seismicity observed is on the near side, with the exception of a couple deep moonquake clusters that move over to the far side. And so the question we have to ask is there a fundamental difference between near and far side, or is this simply an artifact of the detection capability of the Apollo instruments due to deep mantle attenuation, not letting us see far side paths as well? And so by going to the far side, we can directly record far side seismicity, as well as recording or not the known repeating deep moonquake locations on the near side, which lets us constrain that deep mantle structure and understand what we're looking at in a much more clear way. Schrödinger crater is a fascinating site. I mean, over here you can see it's just a beautiful crater with a nice peak ring. It's very clear and sitting right on the edge of the South Pole Aitken Basin. So it's a beautiful crater within a larger crater. It's got smooth floors that are likely impact melts. It's a really interesting location in and of itself. And with our recordings, we should be able to look at techniques like receiver functions, which look at conversions of stuff coming through the crust underneath the site. This is some example of some work we've done on Mars like this, and similar work has been done with the Apollo records, but we are looking forward to getting this with modern clear instrumentation. And there's lots of different ways we can try to look at the local crustal structure, which then lets us think about Schrödinger crater itself, but also link into the larger gravity-derived models for the whole lunar surface. The background noise is also a really important thing to say. As I said, the Apollo instruments were actually limited by that coarse digitization. So we didn't record the background noise in most places. We just got the instrument noise. But the vertical VBB is these two blue lines. These are estimated sensitivity and displacement compared to Apollo. So we're pushing down the noise floor of the instrument itself, which lets us hopefully measure the lunar noise floor, or at least put a new lower upper bound for what that lunar noise level is. And the prediction is that noise level is actually driven by the more or less continuous impacts of micrometeorites. So this lets us directly link to the micrometeorite impact rate, which is actually not all that well constrained. And of course, that's a pretty important goal for understanding if we're looking at long-term human safety for human occupation of the moons, because those little micrometeorites are going to be impacting everything on the surface. One of the first questions that always comes up is you may have noticed in the pictures that the package is sitting on the lander deck, and we'll be recording through the lander. If for those who have paid attention to planetary seismology, both the Viking mission and the InSight mission before deployment taught us that deck-mounted seismometer is a problem, and that is true. So here's the seismometer on Viking, which never actually recorded a Mars quake, or possibly only recorded one. And but we did some analog experiments sticking seismometers on the deck of the Curiosity rover engineering model in the Mars yard at JPL, and another one immediately below, and across the frequency band that starts below the lowest resonant frequency of the lander and down to 30-second period or so, we actually got very clear coherence between the two records. The recording on the deck was effectively identical to the recording on the ground. It could record seismicity on Earth quite clearly. But one thing we noticed interesting is during the day, we had some decorrelation because of the activity of the air conditioning in the hangar where the engineering model was stored. And this is totally analogous to the problems faced by Viking and InSight, which were related to wind. Of course, that's not a problem on the moon. There is no wind. However, we will be having to deal with thermal noise at dusk and dawn. This is analogous to the thermal moonquakes that are actually measured by Apollo instruments that were put well away. But we'll lose some data around that time, and we'll lose some data at high frequency above the resonant frequency of the lander, but we should be able to record good data across a broad frequency band and during the times away from large temperature changes. A little bit more about the seismometer. This is a flight spare very broadband seismometer from the InSight mission, rotated to measure vertical instead of at a tilted axis. With a spring change required to account for the different gravity on the moon compared to Mars. This is contributed by CNES in partnership with IPG Paris. And so this will be delivered and give us very high sensitivity. The 3-component short period seismometer looks like this. It's set up in a Galperin configuration with 3 tilted seismometers that all measure a tilted axis, so they're all identical, but you can combine them to get the full 3-component system. It's a new build, but it's based on the InSight heritage. And this one will be directly delivered by Kinemetrics Incorporated, which is a leading manufacturer of seismometers and seismic data equipment, and is in collaboration with Oxford and Imperial College London. And this is a micro machine silicon system. Just a little bit more about the sensitivity here. These are some plots of this compared to what we believe our requirements are to get the number of moonquake recordings we're expecting, and compared to some of the Apollo data here, and we're really looking forward to getting this high quality data on the moon. The package design, as I said, is a pretty innovative system. And it's basically a box within a box with spacerless multi-layer insulation put in between the two boxes, which gives us excellent thermal control, and that lets us stay warm through the night. And so the batteries function well at the warm temperatures, and we can maintain operation through the night, running at about 5 watts, which is to keep the instruments running, and all they're doing is passively running and recording the data, and then during the day, the command and data handling system kicks in and does comm activities, et cetera, communicating with the planned relay satellite. And that all of the command and communications and power systems are based on Marco flight spares, and they'll be delivered by the group led by Jamie Cutler at the University of Michigan. I'm flying through this, but let's see here. So the one question you might ask, given what I'm talking about here and what Bob Gribb's going to talk about next, an interesting thing here is that this PRISM-1B mission to Schrodinger crater includes Farside Seismic Suite, which has the 2 different seismometers. There's also Litmus, which will include a magnetotelluric measuring system and a heat flow measurement system, and Lucy, which is led by Stuart Bale out of Berkeley, which will have a lot of magnetic measuring equipment, electromagnetic measuring equipment. And by combining all of these, we've actually got most of the primary instrumentation, or something analogous to the primary instrumentation proposed for the Lunar Geophysical Network, which was recently re-explored in a planetary mission concept study led by Clive Neal last year. And I think it's worth mentioning that this is exciting, because this means is effectively somewhat of a test node for a potential future lunar geophysical network. It has, and we've carefully defined some great science goals that we can reach with a single relatively short-lived station, but a long-lived network still, I think, is an important goal for the future of exploration science on the moon. We with a network, we can locate events much more reliably and have many more events to look at, and the long-lived network data samples the whole moon, and whereas we're only focusing on the one area we can really access with the Schrodinger crater site. But this idea is that this can be a key pathfinder for LGN. So we can look at some of the trade-offs of an undeployed package. Obviously, InSight has taught us that deploying to the surface is helpful, but this lets us quantify the trade-offs of that, because there are big cost differences between having a whole robotic system for deployment or remaining mounted on the lander. And this lets us demonstrate the instrumentation, and the system we've got for night survival and long-term operation is a system that could be used either within the context of LGN or in future PRISM missions with other instrument suites. So this is exciting in a lot of those ways. So just to summarize it all up here. far-side seismic suite were designed to go to the moon, outlive the commercial lander delivery system, and we're looking at some key lunar science from the far side of the moon. And so we're looking at far-side seismicity rate. Is there a difference between the near side and the far side, or is this due to deep mantle attenuation? Looking at the crustal structure at both local and global scales, and looking at this micrometeorite impact rate through the background seismic noise. This is the combination of instruments are very complementary on PRISM 1B, and so I'm really looking forward to have this geophysical package delivered to the far side of the moon. Okay, thanks a lot.
Well, it's very exciting, Mark. Thank you very much. Next up, we have Robert. Robert, can go
Hello,
ahead.
can you hear me? Just get the screen sharing here. Okay, are we up with full screen?
Looks great. Perfect.
Very good. Well, thank you for the invitation to speak today about litmus. And I'd like to acknowledge our whole team, especially my partner, Steichi Nagahara, who's also on the call today and can take questions later about the heat flow part of the experiment. Rather than sort of get into the science goals first, I want to show you the sort of hierarchical layout of what is really a virtual suite for litmus. So the first instrument, called LISTER, measures the heat flow of the interior of the moon by measuring the temperature and the thermal conductivity at depths up to 3 meters. I'll show some details of this later, but you can see on our sort of notional mini lander there, it's mounted on the bottom of the lander, and it extends its probe into the subsurface. The other measurement that we make is the electrical conductivity profile of the deep interior to hundreds of kilometers down using what's known as the magnetotelluric method. I'll have a separate slide on this in a moment, but for now, just realize that you have to measure the electric and the magnetic field at the surface of a planet. And so one of the instructions in the call was that you could not interfere or overlap with the Lucy experiment, still already mentioned by Mark. That's quote pre-manifested for this mission. They have a suite of electric and magnetic field sensors that partially overlap with what our magnetotelluric instrument would do. So our solution was to directly partner with them. We will use their magnetometer data. They have both a search coil magnetometer for higher frequencies and a flux gate, analogous to what Dave talked about for Vertex for low frequencies. The cooperation is explicit though, in that in order to get the proper correlation between the electric and magnetic fields, we're going to take a timing signal from Lucy that we can use to correlate the fields once they're received separately on the ground. The thing that we still do is to measure the electric field differently from Lucy. Lucy has these booms that measure fields into the megahertz range for space physics and radio astronomy. We are interested in electric fields that are very slowly varying, typically at less than a hertz. And in order to do that, we need ground contacting electrodes that are spread much farther apart. And I'll show you that mechanism in a moment, but they actually will go 20 meters away from the lander for a tip-to-tip distance of 40 meters. The advantage of using heat flow and electrical conductivity together is that, as illustrated in the data flow diagram, this will help us separate the temperature and compositional dependence as intrinsic to each. So the heat flow is a boundary condition that you can generate a temperature profile from. The electrical conductivity, you can generate a temperature profile assuming you know what the materials are. And so by using these together, we can help deconvolve their dependencies. Now, I will point out that we can't tell difference between, say, olivine and pyroxene, but the electrical conductivity is sensitive to the total iron content, or reciprocally the magnesium number. So we hope to understand something with the magnesium number of the mantle beneath the landing sites, and then also water content. The hundreds of ppm are inferred for at least parts of the lunar interior, perhaps especially those associated with pyroclastic volcanism. And so the water content is something we'll also be sensitive to at significant depth. An advantage of both of these approaches is that we can do these experiments within the daylight mission that's allocated. So it's critical for the seismometer to be able to last longer, but we're confident we can get our work done in the 1 to 2 weeks of the landed mission. Let me just say a few things about MT. It's a passive method. We're measuring natural low frequency electric and magnetic fields. It's been used on Earth since the 1950s. It's basically a version of Ohm's law. You're determining resistance from the ratio of voltage to current. The electric field is determined by the voltage drop between widely spaced probes, and the magnetic field is actually measured the total current flowing. And so, but we get this resistance or resistivity as a function of frequency. Each frequency has a different effective skin depth in the ground, as illustrated in the lower left. And so from that, you can reconstruct the profile of resistivity or conductivity with depth. This is, like I said, it's been widely used on the Earth, but it's new to planetary science, and it's going to be better than prior measurements at the moon, which were done using something called the magnetic transfer function. This is where you just compare the source field, a distant measurement, was done by a spacecraft called Explorer 35, to a surface measurement, at that time was done by Apollo 12. And you can derive what the induced field is, and hence what the resistivity structure is. The advantage of MT is, of course, we don't need this distant observation. And more importantly, it's largely insensitive to plasma distortions that are introduced by finite plasma wavelengths. When the wavelength in the plasma becomes comparable to the circumference of the planet, you start to get higher order effects that never were satisfactorily taken out in the earlier data. For us, this means that we can probe at shallow depths. The higher frequencies have shallower sensitivity, and so we should be able to get at the moon between depths of maybe 100 kilometers down to 800 or more kilometers, really resolving that critical upper mantle region. Here are LISTER, the heat flow probe on the left, and LMS in a different incarnation on the right during some prototype testing. LISTER is a really novel instrument in that it is a pneumatic drill. It does not hammer, it does not rotate, it just inserts a tube and injects gas, high pressure gas, that blows the regolith out of the hole. So you can see some tests at Honeybee being performed on the left. The one in the middle bottom there shows the plume of debris coming up and hitting a dust shield. And then you can see the pile of debris that's produced. In this particular test, they're using some rock chips of centimeter size to show they can loft those out. There's also an approach to dealing with somewhat larger rocks that they call dithering, where they will move the tube up and down while injecting gas, and this, trying to work the flexible tube around a rock. If you get into a rock that's much bigger than you can go around, then I'd say you probably landed in the wrong place. On the right is LMS under some prototype development for Europa. It's the Europa magnetotelluric sounder going in the thermal vacuum at the top. And on the bottom is a sequence that shows our novel electrode deployment system done by Heliospace Corporation. So the little gold thing in panel B that's ejected is the electrode itself. That's the voltage probe. And then there's a place where the cable is wound around it, and the whole thing is released by a spring that's held by a non-explosive actuator, a frangibolt. So these will be held in place until they're deployed on the planetary surface here at the moon. So now I can talk about our science. Our science is pretty aspirational. We really think we can go after some basic questions about the moon. And the first one is vertical differentiation. So, you're all aware of the basic primary differentiation of the moon. The fractional crystallization in the mantle led to stratification. that is thought to be unstable and should have overturned, mixing the interior. But there's a very interesting paper by Moriarty and colleagues that came out last year that looking at SPA, they suggest that the uppermost mantle is still stratified iron-rich cumulates and indeed is creep-rich. So that suggests that the creep was globally distributed and that the overturn may have been incomplete or sluggish, at least at the time that SPA formed. So we think we can distinguish at least these two end members, intellectual conductivity. In the bottom panel there, the red profile is a well-mixed mantle. There's an assumed temperature profile, but it's all uniform magnesium number. And then the green profile is a stratified structure from this Johnson et al. Paper that's stratified by magnesium number, by iron content. And you can see that there's layering and inflection in it, where the conductivity is higher at shallow depth and lower at greater depth because of the uneven distribution of iron. And then just as I mentioned, we would anchor this profile with the heat flow measurement. Our second goal is to look at the lateral asymmetry of the moon. You're all aware that the Maria are concentrated on the western near side. That's what gives us the man in the moon. We know this is a region that's rich in thorium and from Apollo incompatible elements, creep. This is thought to be related to the dregs of the magma ocean, but we don't really understand what the interior structure is. Mark Wazorek and Roger Phillips did a paper 2 decades ago now, where they modeled a large thermal anomaly in the upper mantle beneath PKT that explains the heat flow in Apollo 15 and Apollo 17, as well as long-lived volcanism in that region, but doesn't really satisfy the gravity and topography, namely that there's no real anomaly, whereas this large thermal anomaly should produce some observable signature. Some years later, I published an alternative model where the creep is basically confined to the crust, and that I can reproduce the heat flows at Apollo 15 and 17, but not so much of the long-lived volcanism. And so understanding what the mantle structure is beneath PKT, whether it's hot or cold, is important. And the way we can do this is by measuring these parameters far away from PKT. We have the heat flow on the edge at Apollo 15. We have a electrical conductivity profile at Apollo 12. If we get far away, especially at a place like Schrodinger, we can understand what the true background of the moon is, and then see if PKT is anomalous at depth or not. Our last objective is to understand thermal structure and evolution. You can write the heat flow of the moon as a combination of contributions from the mantle, the crust, and a creep component. And assuming that the creep is proportional to what we see at the surface, there's some absolute scaling factor we'd like to know. But if it's proportional to that, we can solve for these three from using Apollo 15, Apollo 17, and Schrodinger, assuming that there's one background contribution. If there's not, then that's where the electrical conductivity comes in a particular way, is by understanding the difference in mantle temperature between the two from the electrical conductivity. We'd also like to look at the thermal profile. Thermal evolution models make predictions based on the total heat budget and the mantle viscosity. So the slope of the stagnant lid can be well constrained from heat flow, whereas the temperature of the convecting interior will be determined by electrical conductivity. We should be sensitive down to about 800 or 1,000 kilometers. So we will get into that isothermal core down there. What about Schrodinger? Well, this was selected by NASA as a result of many scientists putting a pool in of places they'd like to go to. There's a lot of great geological reasons to visit Schrodinger, but it turns out to be a good geophysical site as well. As I mentioned, it's far from PKT, so we can really establish those background properties of the mantle. The peak ring structure gives us two different choices of crustal thickness, both of which are different from prior landing sites, and thus will help the heat flow problem. Of course, the final site will presumably be negotiated among all the payloads. it's on the rim of SPA, which is an even larger probe into the moon, as we talked about earlier. Interestingly enough, the electroconductivity measurement is sensitive laterally to a depth about to a depth comparable to its it's laterally sensitive to a distance comparable to its investigation depth. So picture sort of a cone. And that means that if we're probing down many hundreds of kilometers, part of that signature will come from SPA. And because we measure in orthogonal directions the electroconductivity, we can determine the anisotropy of the response and see if there's a different response coming from SPA. Lastly, there's local pyroclastic volcanism. Of course, the thermal anomalies long decayed since the Imbrian, but as I mentioned, water is, there's sensitivity to water in these electroconductivity measurements. And if there's a source zone, we may be able to image that. We picked Schrodinger for these reasons, and specifically because it's not Reiner Gamma. Reiner Gamma is about the last place we'd want to go, at least in the early phases of these experiments. While Vertex, I'm sure, will do a great job in characterizing those fields, they will perturb the sort of plane wave nature of what's coming in that we want to use in the time variable fields. And also those strong fields will take us out of the very sensitive gain range that we want to use in order to make these time varying measurements. So to wrap up, I kind of alluded this to earlier, but both Lister and LMS are previously and independently selected under CLIPS under the LSAT-P program for the 19D mission. And it was indeed our serendipitous selection that got Seiichi and I to want to collaborate both on this mission and for PRISM. The 19D mission also has a retroreflector, another important element of a lunar geophysical network, and the PRISM launch will probably not occur until 2025 in order to meet LUCI requirements for radio astronomy. Mark talked about the seismic suite. We were equally thrilled that we have sort of a complete geophysical package here of the kind that we've been talking about for the LGN. And although the LGN, of course, has to be competed, it is a big step beyond what we can do under CLIPS, principally for seismology, but also we'd like to do longer term monitoring for these other techniques, as well as go to our primary sites for LGN, which would include something in the far side, at the thickest crust, someplace like the middle of Mare Imbrium, where it's in the middle of PKT, but there's no creep. So the constraints are different under what we could accomplish synoptically under LGN versus trying to build up as much as we can under CLIPS. So it's going to be an exciting time for geophysics on the moon, I think, among these two missions. And we look forward to working with everybody. So thank you very much.
Thank you very much, Robert. Very exciting as well. Brian, do you have any remarks?
There's been a lot of interesting activity going on in the chat room. You may have missed some of it if you were actually listening to the talk, so it's a little bit of a conflict here, but there are some interesting questions that have come up. One had to do with, let me scan through here, if Mark, can you share any public information or on the design of the FSS thermal enclosure? Surviving the lunar night is an interesting problem to solve.
Yeah, so obviously I don't have the full tech specs here handy, so but we're working, and so this is actually an interesting bit of synchronicity too as well. So people may have seen the PRISM 2 announcement has come out, and one of the tech demos mentioned in there was the palette system led by Dave Bugby, which is actually the same thing we're building on. So there's some information out there about the pallet system, but as I said, the whole system is built on a cube within a cube with tension Kevlar cables separating the two, and a spacerless multi-layer insulation in between. It gets a very low thermal conductivity, and then you combine that with a very efficient thermal switch connected to a parabolic system to get the heat away during the day. So that's the critical components that go in. Stay really warm during the night with a very efficient thermal switch to let the heat get out during the day. So that's yeah, the quick summary. And Ryan posted the Prism 2 solicitation in the chat, so people can look at that as they desire.
Very good. That's an important point. Another one for you, Mark. Is it possible that FSS's resolution will give unambiguous confirmation of the presence or not of a solid inner core within a deep moonquake detection, as opposed to the Apollo seismic data that gave Weber and Garcia models?
I think something like that is likely going to wait for the Lunar Geophysical Network or similar. I'm not, I don't want to overstate what we're going to be able to do because, you may have noticed in the chat, I had some discussion about location. Location is going to be challenging with the single station and with the scattered nature of lunar data. So I don't want to make too many promises on a lot of deep structure. That we can get at the deep mantle attenuation simply by observation or non-observation of the known near-side quakes, but detailed estimation of deep structure really requires well-located events, and we're not going to have as many of those as we would have with a full network.
Very good. Also, again to you, Mark, this is from Elizabeth Fisher. She's wondering what type of gas the pneumatic drill will be injecting into the regolith and whether the chosen site will consider the lunar volatile system.
That's for Bob, not me.
And you're right.
I am so sorry. I'm so sorry.
Let me, if Seiichi Nagahara is on, can you unmute him and let him answer that question, please?
Yeah, we are planning to use nitrogen.
Okay.
For the gas.
And how much?
Oh, sorry. Yeah, I don't have the number. I need to talk to my engineers. Yeah, but it's at least enough to blow a hole 3 meter deep.
So for both Mark and Bob, there was a little bit of a preview of the upcoming negotiations for where in Schrodinger you're going to go. It's clearly a very diverse terrain. Can you talk about perhaps some of the geological characteristics that might inform your decision or position in such a debate?
Go ahead, Mark.
I was just going to say, from the seismology, we're relatively agnostic. We're just very happy to be on the far side, and we'll look for different structure related to the local crustal structure, whether we're inside or outside the peak ring. And so I don't have a strong opinion on that. So I think the bigger concerns are the ones that Bob's going to talk about.
Well, I mean, from your diagram, Mark, you showed, the maybe just schematically kind of near the rim, and I can imagine that, with receiver function, you'd want to try to look at some details of crustal structure that might reveal something about the Schrodinger impact, formation. Of course, getting an excellent high on crustal thickness with Grail is important, and yes, maybe the thicker crust is better for that. I don't know. From the perspective of litmus, again, we're just got to look and see whether we think that the thicker or thinner crust provides the better separation of the heat flow. you know, there's really not much we would do with regard to looking at the impact per se. You know, we might see something of the pyroclastic source if we landed in the inner rim. There are also constraints from the Lucy instrument about, you know, they want to be, you know, in sunlight, you know, for the daylight mission, like we do, but they want Jupiter and Saturn below the horizon. And if there's something about the, you know, the rim profile that gives them, you know, an extra day that way, we may want to position that way. The most important thing in the end, though, Teiichi Nagahara has done an exhaustive study of the landing site possibilities in Mare Crisium, and, you know, getting the best conditions for LISPA in terms of the lowest abundance of surface rocks and subsurface rocks, as best as we can figure out, is going to be tough.
Very good. One for Dave. Just from the evidence that you have right now from remote sensing, how homogeneous or heterogeneous do you think the population of magnetic anomalies is? And if you suspect them to indeed be heterogeneous, what other example site other than Reiner Gamma might you choose, might you wish to see for a future mission to actually compare against what you're about to find at Reiner Gamma?
Well, that's a really interesting question. Probably it would be interesting to go to a highland magnetic anomaly and swirl. You know, there's the idea that a number of the magnetic anomalies are located antipodal to the major basins. Reiner Gamma, however, is not antipodal to one of the major basins. So it's potentially different from other magnetic anomalies in that way. You know, there are some magnetic anomalies that don't have swirls associated with them. So, you know, maybe from what we learned with Lunar Vertex, we'll you know, have a better idea of why that might be, but perhaps go into a magnetic anomaly that doesn't host a swirl.
Excellent. Let's see, Kevin Dupriest asks, do we expect to capture lunar seismic activity with MT data?
Yeah, I responded to that in the chat. We hadn't, you know, I'm aware that there's a lot of work on Earth trying to look for EM signals, especially as precursors of earthquakes. And certainly we hadn't really thought of that. Every quake that FSS picks up, we can look in our time series and see if there's any correlation. So it's a really interesting idea. My only concern is that, you know, we can't really image shallowly with the magnetotelluric instrument because of the bandwidth limitations and how resistive the crust of the moon is. But you know, if there's some kind of signal of a local quake that may not show up in any kind of imaging, but just show up in the data, that'd be very interesting.
I do have one question for Mark, if that's okay. Assuming you would be able to localize one event with a proper certainty, are there any plans to collaborate with AirRock, for example, to image that site before and after event?
Yeah, sure. You know, I actually have already spoken at one of their telecons. We're thinking of ways. So I think there's a lot of interesting collaboration potentials with LROC, either looking for impacts after we observe something, if we happen to observe an impact that we can localize relatively well, or by them seeing an impact and telling us to look for it in the data, so then we know where it is, even though we didn't, you know, couldn't tell from the seismic data alone. It's also interesting to think about collaborating with Earth-based observers like the group out of Marshall that looks for impact flashes. Of course, those are going to be on the near side, but you know, we're not that far from the near side where we are, so it's quite possible that some near side flashes may be associated with things we can see. So observational, visual observation, I think, is going to be really important for helping us out.
That's fantastic.
Well, also in terms of LROC coordination, in addition to impacts, I mean, some of these quake evidences that we have from Apollo are fairly significant in size. And if there is a subsurface quake generated of significant magnitude and we get an idea of location, it might be very interesting to go look for subsequent new rockfall deposits that might have been associated with that quake. I don't know that Valentine would be interested in that, but
exactly. I was thinking about that, Brian. Exactly.
Yeah, I would love if we're lucky enough to get one of the shallow quakes. You know, they happen on the order of several months repeat time, and we're proposing operation for 4 months. So we may not. There's no guarantee whether we'll see one of those or not. But if we do, then that's potentially a really great signal. So I hope we do, and then I hope that can lead to some great observations for LROC.
Okay. Well, I believe we are at time now. So I want to thank everybody for an outstanding panel. This is truly very exciting, and congratulations to each of you for the selection of your suites.
Thanks. It was good to be here and present.
Thank you very much.
Thanks a lot.
Thank you.
Good day, everyone. We're about 5 minutes away from our scheduled start time. I just wanted to remind everyone to keep your cameras off unless you're speaking, and keep your microphones muted unless you're speaking. But when you do speak, please open your microphone and start your cameras. But we're still about 5 more minutes away from our start.
Is my screen sharing?
Yes, it is.
Okay, thanks.
And it looks like we've reached our scheduled start time, so you can begin whenever you're.
Okay, Shuai, are you online?
Yeah, I'm here.
Go for it.
Oh, I thought you want to go. Okay, so hello everyone. Thank you for joining this session. I'm the chair. I'm very happy to be the chair of this session, and just want the speaker know, as you may know already. So each one will have 10 minutes for their talk. I will remind you, like on the 8 minutes for 2 minutes remaining warning. So I think we can start now. Is that okay? Eric, do you have anything else you want to say?
No, that sounds great. Thank you.
Okay. Yeah. So everyone, if you have a question, please post in the chat window. If we have time, we can ask them to answer. If not, we can discuss later this session. So today, the first talk will be given by Ariel Deutsch, and their title of the talk is Roughness Measurements of Ice-bearing Craters on Mercury and the Moon. So take it away, Ariel.
Okay, thanks, Shuai. Okay, so we're all super interested in permanently shadowed regions, or PSRs, and you can see them highlighted here for the north poles of Mercury and the Moon. But even though Mercury and the Moon have these similar thermal environments that can host water ice and other volatiles on long-term timescales, the inventories of ice are quite different. And so, for example, polar ice on Mercury appears as these really thick deposits. They're laterally contiguous. They fill individual craters to the boundary of permanent shadow. And in contrast, ice on the Moon appears as these relatively patchy frost detections that occupy only a small fraction of the available cold trapping surface area. Also on Mercury, ice appears to be much more pure than ice on the Moon. So for example, neutron suppression measured by MESSENGER suggests that ice deposits are almost entirely H2O. And in contrast, neutron data of the lunar poles are suggestive of only a few weight % water. And so today we're looking at how these differences affect the surface roughness properties at the poles. And so to measure surface roughness, we're using a standard deviation filtering for relatively flat surfaces, so those with slopes less than 10 degrees. And essentially we take the standard deviation of a local neighborhood and apply that value to the central pixel of the neighborhood, and then continue that process through a moving window across a DEM. And just a really simple example is shown below, where what would happen is the exterior of a pineapple is relatively rougher in comparison to like a smoother interior of the pineapple. But this metric is size dependent. So if you take a larger neighborhood, or if you have a coarser resolution DEM, then you start to see some of the larger scale topographic variations in the scene. Cool. So on Mercury, we've looked at 6 north polar craters, and these were selected due to the availability of new high resolution DEMs. And the 6 craters that we looked at all host thick, large polar ice deposits, and they're all capped by a layer of low reflectance volatiles. And so you can see an example of that here. The crater outline of Fuller is represented by this circle. And you can see the low reflectance ice deposit both in the visible images and then also in the MLA reflectance data. And you can see the polar deposit has a very distinct geologic contact. And so what's cool about Mercury is that we can analyze how the roughness varies across the polar deposit floor in comparison to the neighboring ice-free portion of the floor. And so for the 6 craters, you see roughness on the y-axis as a function of maximum surface temperature, which is a proxy for the polar deposit location. So we know that low reflectance surfaces terminate at about 350 Kelvin, which is represented by these dashed, or the central dashed lines on the plots. And what we're finding is that generally the polar deposit is relatively smoother in comparison to the other portions of the crater floor. And as an example of more up close, so on the left, we have Angelo crater, where this 350 Kelvin contour separates the polar deposit from the illuminated portion of the crater floor. And again, in roughness temperature space, the polar deposit is relatively smoother in comparison to the warmer portions of the crater floor where ice is absent. And you can also see this in the distribution of roughness values, where the polar deposit at, again, colder temperatures is skewed towards relatively lower roughness values in comparison to the warmer surfaces. So today we don't have a chemical measurement of the low reflectance surfaces, but Hamill et al. Showed that coronine could be a good simple representative for what these low reflectance surfaces are comprised of. And so we used the ice stability models from Hamill et al. And looked at them in comparison to our roughness values. What we're seeing is that the smoother polar surfaces are generally correlated with regions where coronine is stable at the surface. And so all of those surface stability regions are shaded here in the plots. Okay, so for the moon, on the moon, we don't have these thick surface deposits like we have on Mercury, but there are some observations that potentially thick layers of ice-rich materials are present below the surface. And this is interpreted from shallowing of polar craters. And so if thick ice-bearing craters could influence crater morphometry, is it possible that these icy materials could also influence surface texture? And so for the moon, we've looked at 12 polar craters so far, 6 at the North Pole, 6 at the South Pole. And this population includes craters that both do and don't have ice detections, although I think we'll hear a little bit more about this from Miriam later in the session. Okay, so we compare roughness inside ice stability zones and outside ice stability zones, which we denote by temperatures less than or greater than 112 Kelvin. And this is because, again, on the moon, we don't have these thick deposits. So we're looking at zonal statistics here. And what we find is that the roughness values in these two zones are statistically differentiable. And specifically in 9 of the 12 craters we've looked at so far, the ice stability zones are relatively smoother than the non-ice stability zones. But interestingly, these 9 craters include both craters that host ice detections and then also craters that don't host ice detections, suggesting it's not surface ice that would be affecting the roughness here like it is on Mercury. So potentially there's some sort of deeper ice affecting the overlying signal. And so we've looked at the LPNS signal, which can help constrain the abundance of possible ice down to about 1 meter. And we found that ice stability zones tend to be correlated with relatively higher hydrogen content, and specifically for each of the craters that show a smoothing in the ice stability zone. However, here's an example for Amundsen. You can see that still the modeled hydrogen is really, really low. And so probably can't account for all the smoothing that we're seeing, but perhaps the signal that we're looking at is from ice concentrated below the sensing depth of LPNS. So in conclusion, what we're finding so far is that on Mercury, polar deposits are distinctly smoother than the ice-free portions of the crater floors. And this is likely due to the superposition of several meters of surface ice. On the moon, it's a little bit trickier. We're using zonal statistics, but we're finding that inside and outside ice stability zones can be differentiated. And potentially this could be correlated with the presence of subsurface ice. But overall, there's more work needed to understand the relationship between surface and near surface and deeper ice. And we're looking forward to future exploration to help with this. Thank you.
Great. I have tons of time left.
Oh,
I think I started 1 minute later. So.
Well, I heard your talk is a little long, Shuai, so we can share.
Okay. Oh, thank you. I'm so glad to take extra minutes. So should we move on?
Yep, sounds good. And just a reminder to everyone, we can put chats in the questions in the chat with a Q, and then we'll also have time at the end for a lot of discussion with all of the speakers. Okay, so next we have my co-chair Shuai Li, who will be presenting on characterizing potential landing sites for future exploration of lunar surface water ice. Go ahead.
Okay, thank you, Ariel. So as we know, the surface exposed water ice was recently found in some lunar PSRs. Here's the map on your right side, North Pole and South Pole. We know it is important for in situ resource utilization, and also those ice may still preserve the features of their origins that may help to reveal the origins of water on the moon and the Earth and even the inner solar system. However, PSRs reaching in water ice exposures are still lack of some detailed information for future exploration, particularly the ice content at each PSR and also the associated mineralogy. We still need further studies. And also, most important, how to estimate the water ice in the ice regolith mixtures has not been well studied, particularly when the ice abundance is low. That's the focus of this work. And also it is important for estimating ice for future mission data, such as Viper and Trailblazer will be launched soon. And the PSR is hosting abundant surface ices are potential landing sites for future exploration. And the data, uncubed moon mineralogy mapper data used in this study at each PSR can be averaged to reduce the noise level. And then we can use the data to estimate the ice content and the mineralogy information. Here's one example at the Shoemaker PSR as shown here. The black curve is the average spectra of the whole PSR. You can see the prominent feature near 1 micron absorption, and also lack of a 2 micron absorption. And also we can average the m-cube pixel showing ice features as shown in the blue line. You can see the ice absorptions near 1.5 and 2 micron. The red curve is the average spectra near the crater rim. It's relatively featureless. Anyway, we can use this spectra to tell their ice content and mineral information. And the question is like which kind of which features or what features we should use to estimate ice content from the observed data we have now. So here's the plot. I'm showing the spectra of pure ice as a blue line in comparison to the spectra of 2 Apollo samples, Apollo 11 sample and Apollo 16 sample. It shows very diagnostic absorption features in comparison to the typical lunar surface regolith. I'm going to introduce from the left, from the right to left, try to tell which will be the best to we can use to quantify the surface water ice. The first one is the molecular water bending absorption near 6 micron. It is very sensitive. This is fundamental. So this is very sensitive to the presence of molecular water. And the 4.5 micron absorption is the combination of molecular water bending and also the lattice vibration. They're also very strong. The strongest is near the 3 micron. Is due to the fundamental stretching of OH and all the presence of molecular water overtones. So because this absorption can be caused by both hydroxyl and molecular water, so it is very difficult and challenging to identify or discriminate whether molecular water present if you just solely use the 3 micron bands. And another one is also very strong. That's near 2 micron. This is due to the combination of OH stretching and the molecular water bending. So if you see a 2 micron feature like this, it can tell you the presence of molecular water. So that's the focus of the study. We're going to use a 2 micron feature. And again, the 1.5 micron can also be caused by both hydroxyl or molecular water. So it's not unique to identify molecular water. And the reflectance in the mid IR feature is relatively low in comparison to visible. So maybe the emission spectra will be more useful than reflectance. Again, the focus of this work will be estimating ice content from the 2 micron absorption, and we use 2 different ways to quantify the ice content. First, we use the radiative transfer modeling to mix the ice and the regolith intermittently, and we use Hacking model and assume the particle size at the mean particle size measured from Apollo samples. And in this plot, I'm showing the inner members. This is the blue line is the pure ice, and the dark red line is Apollo 16 sample, and also a lunar analog sample, more glass, and also Apollo 11 sample. Here on the top right, I'm showing one example of adding more ice to the Apollo soils. You can see the change of the 2 micron absorption features stronger and stronger. And we can correlate with the band depth at a 2 micron with the ice content as shown in the bottom plot. You can see no matter which sample we use, the trend is very tight between the ice content and the band depth at a 2 micron, strong indicating we can use the 2 micron feature to identify water ice. And the second way, we did experiments in lab to mix real water ice with lunar analog, the Morph glass. So the Morph glass spectra is shown in the left plot, and this in the middle plot, I'm showing the lab prepared water ice. You can see the absorption feature changes as you change the particle size. So that's why the particle size is important. Again, we assume the mean particle size as 70 micron as the mean particle size measured from Apollo samples. On the top red figure, I'm showing how the spectrum looks like when mixing ice and the basalt sample. And at the bottom right, I'm showing the correlation between the ice content and the band depth at a 2 micron. Again, you can see the trend is very tight. So put together, we can develop an empirical model for estimating water ice content from 2 micron absorption. As shown in the left figure, you can see both experiments and simulations, they follow on the same trend. And then we can derive this empirical correlation between ice content and the band depth. And this is very useful to determine the detection limit of water ice based on the 2 micron absorption with the given SNR as shown in the red plot. So for like a 1% detection limit, you may need like around 100 SNR, signal to noise ratio. And also it could be very useful for interpreting 2 micron absorption features of future mission data, for example, Viper or Trailblazer, because they all have measurements at this wavelength range. And then we can use the model to estimate the ice content at a Shoemaker PSR. This is the average spectrum and cube spectrum of all ice-bearing pixels. And we can have 2 different scenarios. Conservative scenario, we can assume like, you know, the part of the absorption is due to the noise, and we can roughly estimate the band depth. And also realistic scenario, we use the mean value to estimate band depth. So it gives you like around in the red dash box, give you around a 5 weight percent to like a 40 weight percent ice. And also we can tell the mineralogy from the average and cube data. Again, this is a scatter light, so we cannot tell exactly the true continuum and also absorption shape, but a major feature should be there. And we compared it with the spectra of glasses found in Apollo samples like agglutinates and Apollo orange glass. You can see they show a broad 1 micron absorption feature and a lack of 2 micron feature, suggesting dominantly glass. And future high quality data may help to validate the MQ observations. So in summary, a model is developed to derive water content from the 2 micron absorption features. Now the model can be used to assess the detection limit of water ice with the given SNR, and important for interpreting data for future missions. And particle size regulates composition maturity and beam geometry will be considered in future studies.
the Shoemaker PSR we get is like at least a few with % of water ice and the regulated dominant glasses. And we will perform data studies for remaining 8 PSRs for future exploration of lunar surface ice. Okay, thank you.
Thanks, Shuai. You have a question in the chat from Paul Hain, but I suggest maybe we'll save that for the discussion. You can also look at it in the chat, and we'll go on to our next speaker to stay on schedule. Cool, thank you.
Okay, can you hear me well?
Yes. So our next speaker is Miriam Lamelin, who will be presenting investigating water ice detections in lunar permanently shadowed regions using the Kaguya spectral profiler data. And
all right,
look good, thank you.
Still looking good, thank you. All right, so I'm excited to present some preliminary results today, looking at potential water ice detection in PSRs using the Kaguya spectral profiler data. So it's work that's been conducted at the University of Sherbrooke and the University of Hawaii. So as you all know, the analysis of various remote sensing data sets point towards the presence of water ice at the surface of some, but not all PSRs, and in a somewhat patchy distribution. Two of the recent observations have been made by LAMP and LOLA on board LRO. So on the left, you can see the LAMP off and on UV band ratio, the anomalous values. And in the center, you can see the anomalous high 1064 nanometer reflectance from LOLA. And in both of these cases, the anomalous reflectance value were mostly associated with surfaces that are consistently colder than about 110 Kelvin. So that led towards the thinking that most of these detections are probably related to the presence of water ice, although some other phenomenon might be responsible to another extent, such as mass wasting and increased porosity or a reduced degree of space weathering. And then more recently, Lee et al. Analyzed the data from the moon mineralogy mapper, the hyperspectral data, and detected the presence of the 1.3, 1.5, and 2 micron absorption bands that are attributed to water ice in many of the PSRs. So you can see the map on the left. And most of these locations are also co-located with the anomalous LAMP and LOLA detections, and with surfaces consistently colder than 110 Kelvin, which really strengthened the case for the presence of superficial water ice there in these pixels. However, when we look at the 3 data sets together, the M-Cube, LAMP, and LOLA, we can see then they generally agree very well, but there are some notable differences. So for example, M-Cube did not see any water in Amundsen, Edervari, Idelson L, and Vichert, whereas LAMP and LOLA potentially did. So there are 2 potential explanations to this. The first one is that there is indeed no water ice in these craters, and the anomalous LAMP and LOLA detections can be attributed to other phenomena, such as the mass wasting, porosity, or space weathering. And another option is that there is water ice, but M-Cube might not have detected it. Why? Well, because the M-Cube detection were restricted to the optical period 2C, which spans a really short time frame between May and August 2009. So it's possible that within these few months, maybe the illumination was not ideal to see water ice there. So our objective was to investigate the presence of water ice using an independent data set, so the Kaguya spectral profiler data, and using the same method as Lee et al. Did. So the SP is a point spectrometer that acquired data in the visible to near infrared between 0.5 to 2.6 microns. It has a spatial resolution of about 500 meters per pixel, which is coarser than M-Cube. but it acquired data during approximately 2 years between 2007 and 2009, which resulted in over 7,000 orbits of data and millions of polar acquisitions to look at. So for each orbit of data, we extracted the measurements that are located poleward of 65 degrees in latitude. And then we determined if each point falls within a PSR or not. If it fell within a PSR, then we calculated the true reflectance as Lee et al. Did. So we accounted for the fact that the reflectance has bounced off from the crater wall, and we removed that contribution to the reflectance to really highlight the spectra that's inherent from the PSR itself. Then we removed the continuum around the absorption bands at 1.3 and 1.5 microns. Unfortunately, the data near 2 micron was too noisy in most cases to detect the absorption bands there, so we focus on the 2 other ones. And then we calculated the spectral angle and the correlation between each SP spectrum and the spectrum of pure water ice. So here you can see the preliminary results for the first 1,000 of orbits that we looked at. On the left, you can see the histogram of the spectral angle versus the normalized frequency for the sunlit pixels in black versus the PSR pixels in blue. So if we assume that the sunlit pixels are too warm to host water ice, it appears valid to assume that pixels with a spectral angle shallower than 30 degrees might host ice. And we can see somewhat the local mode here happening in the PSR pixels at spectral angle shallower than 30 degrees, which in fact is the same cutoff that was used by M-Cube to determine if there's potentially ice or not. So that's a good point there. Then on the right, you can see the histogram for only the PSR pixels, but broken into different spectral angle. So the blue solid line represents the PSR pixels with a spectral angle that's greater than 30 degrees. And their correlation is mostly negative or very weak. So it makes sense to assume that there's most likely no water ice there. But if we look at the pixels with spectral angle shallower than 30 degrees, then we can see this somewhat bimodal distribution with correlation that's really high around 0.9 and another peak at around 0.6. So we still have to look into that, but it appears that the local maximum at 0.9 is for pixels that have a relatively strong signal versus the lower peak at around 0.6 is for pixels that have a somewhat higher noise level. Then here's what it looks like in terms of spectra. You can see 2 examples of pixels in PSRs with spectral angle shallower than 30 degrees and high correlation coefficients. The dashed line represents the pure water ice from USGS, and the solid line represents the scaled reflectance from SP. So in both of these cases, we can see nice absorption bands near 1.3 and 1.5 microns. And we also even see the very weak absorption bands between 1 and 1.1 microns. Now, here's what it looks like in terms of location for both the South and North Pole, but still only for the first 1,000 of orbits. So all the blue points represent the spectral angle shallower than 30 degrees, where ice might be potentially present. The 2 stars represent the spectra that we've seen. And we also see potential detections in Amundsen and Eder-Vari. So in conclusion, the Kaguya Spectral Profiler really allows to look for water ice in PSRs via at least the 1.3 and 1.5 micron bands. In the future, we'll see if we can also use the 1.1 and the 2 micron band potentially. Spectral angle shallower than 30 degrees seems to be indicative of the potential presence of water ice. We will also investigate other metrics such as the correlation and the band depth of the different absorption bands. And we will complete the analysis of the remaining orbits of data and compare with M-Cube, LOLA, LAMP, and Diviner. and also look for variations in time since we have two full year of data. And that's it. Thank you.
Thank you so much, Miriam. Okay, so for the time, I think we're going to go to the next speaker, but you do have some questions in the chat and then we can regroup during discussion period. So our next speaker is Alex Schelke, who will be presenting on lunar cold traps, prospecting by thermoluminescence. And we can see your slides, they look great.
Perfect. So just now, hope you can hear me too. I believe
so.
So.
Thank you.
Great. So with this talk, I want to bring TL into the picture of prospecting cold traps on the moon and evaluating their thermal history. And briefly, because we have heard a lot about PSRs before, but that's an important part of this talk is some information that are necessary are that they're located at the poles, they're thought to harbor water ice and other volatiles because they have temperatures down to 30 Kelvin. And one thing that needs to be said is that those are either measured or modeled at the current time. There are also many unmapped cold traps that exist on many scales from a kilometer down to the centimeter scale. And with them being on the lunar surface, they substantially augment the areas where ice, water ice, or other volatiles could have accumulated. If we're talking about accumulation of water, obviously, we also need to think about what the kinetics are. So the water, or the mean residence time of water, depends on the temperature, and there is a boundary essentially that allows us to infer that the mean residence time of water is up to billions of years at the right conditions. And it's also a reminder that the buildup of water is a very slow process. It happens over millions of years. Talking about the history of cold traps, so we should also remember that the lunar surface is a dynamic place, as shown in figure 6 on the bottom left figure there, where we can see a landslide deposit at the south massif in the Taurus Littrow Valley on the moon. And if you're looking at one of these PSRs, for example, Shackleton Crater, we can see there's a lot of stuff going on around, many impact craters, but also right at the rim. And there most likely are geological processes that disturb the thermal regime within the PSRs. When we have those impacts, we have dust movement, probably boulders that move into the cold, and they will redeposit, and they will be at a different temperature because they're exposed to the sunlight. So any introduction of that material into the PSR may have an effect on the volatile deposits, which may sublime, escape, or recondense if the conditions were suitable. And that this can be a problem is shown on the right-hand side in these graphs. Just to summarize, if we're having a temperature amplitude of about 5 Kelvin right at the border of where water is stable on the moon, we can lose our ice layer on the top of the surface of the regolith, and that penetrates down into the depth too. So we would change or affect the ice density in the regolith because of a thermal anomaly. And any of these observed model temperatures really won't tell us something about the temperature history. Is it okay to assume that that temperature history in these PSR is uniform when we already know that the temperature distribution is not? So any model temperatures alone may not be indicative enough of how well volatiles are preserved. And that becomes a problem if we're having data sets where we're inferring that they're volatiles, but they're inconclusive or they're troublesome, and we cannot measure the volatiles directly in these PSRs. So we should have a method to at least figure out what the thermal history was to make an evaluation. And one way to do this would be thermoluminescence, and it can give such information on the scale of several 100 million years, which is that scale where water sublimes or recondenses or builds up in the lunar regolith. Talking about thermoluminescence now, I should tell you what that really is. It is a physical state process. Essentially, you have your regolith sitting on the moon. It's in its radiation environment. And with that, ionizing radiation, the electrons in the solid will be reconfigured into higher energy bands, or energy states, I should say. And they can be trapped there. They will hang out there, and that buildup will be a condition of the equilibrium temperature. So it's in equilibrium with its ambient temperature. So the type of energy traps that are stored within a sample reflects the thermal history. Now you can take a sample, as we do this right now, and you take it to the lab and you heat it up in an oven, and you would provide that excess energy that it needs, that activation energy, to get out of that trap, to fall back into its ground state. And while it's falling back, it will emit light to get rid of that excess energy, which you can measure. So on the left side is a theoretical glow curve in black as a function of temperature and the intensity of light that would be measured. And what I really just want to say is that the shape and the intensity of a glow curve depends on what kind of electron traps are stored in that sample. To give you a better idea, here's a real world example of TL measurements for lunar samples done in the 70s. And I'm focusing only on the temperature estimate here in that talk. On the left side, there is a glow curve for a sample that was collected at Station 6 during Apollo 17, Boulder 4, that was in a sunlit area. And that curve, we can see if we measure this sample in TL, you can see that the readout starts somewhere at 500 degree Kelvin. That's when we detect the first light coming off of the sample, and we can do our analysis. We can figure out there's two different type of electron traps filled up in that sample, and we do our math. We get a temperature estimate of around 370 Kelvin. There was also a sample collected not really far away, but it was located in the shade, and that glow curve is shown on the right side, which shows that it looks much different. It has a different shape, its intensity is different, and in particular here, the readout starts somewhere around 400 degree Kelvin because there's an initial or an additional electron trap present here at a lower temperature that is a lower energy trap. And we do our math again, do our analysis, and it would spit out a temperature of around 255 Kelvin, where that sample was stored for about 50,000 years. So that's what you can do with the glow curve analysis. Now for lunar cold trap prospecting, what would we expect? We have never really done one, of course. So what I'm showing on the bottom is, again, a theoretical glow curve for a lunar sample in comparison to the both that I've already shown. And what we expect is, being consistent with what I said before, that we should have a lower readout temperature when we do a TL measurement and much more underlying peaks. And we can, again, do our analysis to glean all that information from that glow curve. The benefits of in situ prospecting by TL would be that it's in real-time assessment, supports surface operations, eliminates complicated cryosample return to Earth. And then the final question, what will you need to do that on the surface of the moon? We have an idea to build an instrument, which we call THEA. It stands for Thermal History Exploration Instrument for Artemis. And what it is, it's an assembly of components that have already been flight proven by other missions. So it's assembling it into a different configuration. It would be low mass, small size, low power, and low data bandwidth. And to come to a conclusion, the cold traps are numerous. Prospecting is important for lunar exploration and science, and the thermal history of PSRs should also be relevant for assessing the IRCU potential. And TL is suitable for cold trap prospecting. And by the end of the talk, I would have already done 4 glow curves on the surface of the moon. Thank you.
Thank you so much, Alex. We have time for a quick question, and Michael Nord wants to know if this could be done in situ with a laser heat source, or no need to handle the sample, ?
Yes, so I pretty much really just closed the slide, but in our current configuration, we have like a glow oven, which is basically a heating strip, but you can also do a laser impulse to actually heat the sample up. That would be probably work even better because you have to consider like heat conduction in a vacuum. You really have to have good contact of your assemblies of a sample pan and so on. So a laser would probably work much better than what we have thought of.
Great, thanks so much. I think you have some more questions coming in the chat, and then we'll also have the discussion period.
Sure.
Thank you. I think Shwai will continue on.
Yep.
So our next talk will be given by Paoheng, and the title of their talk is Polar Night Vision at the Moon's South Pole, the Lunar Compact Infrared Imaging System. So Paul, please go ahead.
Yeah, I'm trying to share my screen, but it's telling me I can't.
I think, Alex, you have to stop share your screen first, and then, yeah.
Okay, thank you very much. So thanks to the session chairs and also to the conference organizers, especially Ricky and his team. I think, you know, as much as we all miss seeing each other in person, this is about as seamless as a virtual conference can be. So thanks a lot for that. So I'm going to talk about the Lunar Compact Infrared Imaging System, or LSIRIS. Here's the team based at the University of Colorado's Laboratory for Atmospheric and Space Physics, or LASP, and Ball Aerospace, as well as our science team members. So LSIRIS is a thermal infrared radiometer. I'll describe the instruments in more detail in a minute. This was selected through NASA's LSIT-P, or the Lunar Surface and Technology Payloads program, to fly on the CLPS 19C mission. The lander provider is Mast and Space Systems, and our launch was recently pushed to November of 2023, with surface operations in December of that year. I'll talk about the potential science at the landing site, which will be in the South Polar region at a latitude higher than 84 degrees south, and that's still being sort of negotiated, but we do have a notional landing site. So you can see there's a range of different really exciting instruments on this payload. And among those is a thermal infrared camera called LSIRIS, and that's positioned here on the side of one of the lander panels. And we expect to operate on the lunar surface for about half the month during the daylight hours. So the science background for LSIRIS is that we've established, you know, through both remote sensing of the moon and other planetary bodies, including the Earth, the value of thermal infrared remote sensing. So temperature is the primary quantity that we seek to measure with an instrument like Diviner, which is shown in the upper right. Diviner also has shown the way that you can use multiple spectral bands in the thermal IR to do compositional analysis, specifically looking at the silicic or mafic content of the surface materials. And then, of course, the physical properties like density that kind of get folded up into thermal inertia. So that's the types of measurements that get made with thermal IR remote sensing. And I think what Diviner has shown is the need for something like LSIRIS on the lunar surface. And so what we found through Diviner is this extraordinary thermal diversity, which is arguably larger on the moon than anywhere else in the solar system, from less than 30 Kelvin up to more than 410 Kelvin in the lunar pits. And then compositional diversity, things that we didn't necessarily anticipate, like the silicic domes, and then thermophysical diversity, showing the progression or evolution of fresh craters evolving to older craters as the rocky material gets broken down into regolith. And we can, you know, sort of watch this happening, you know, before our eyes effectively through looking at craters of different ages. So this is sort of the background science that shows that there's this extraordinary diversity that you can even see at the orbital scale. And LSIRIS has 3 different science objectives, and I'm going to go through each one of them. So the first objective is to provide ground truth for the compositional investigations like those done by Diviner. So here's an example of a map provided by Ben Greenhagen of the Christiansen feature on the moon, again from Diviner data. You can see this, you know, striking variation in the composition of the lunar surface. We know that there are effects that go into this that have been corrected mostly empirically, and those include surface roughness as well as near surface thermal gradients, basically. And so we've done these sorts of corrections empirically based on what we observe with Diviner. with an instrument down on the surface deployed, taking data at much higher resolution, you could do this using a physical model. So we hope to be able to use the LSIRIS data from the surface to then better understand what we're actually seeing in the diviner data. So we anticipate this kind of feed through or feedback on the diviner data to improve these global maps, as well as those of other instruments like M-cubed in correcting for surface roughness and those other effects in the thermal infrared. And so the three compositional bands for LSIRIS overlap with both diviner and lunar trailblazer. Those are shown on the right-hand plot with the emissivity spectra for different compositions that we anticipate to measure on the surface. The second science objective is related to the first, which is to get down on the surface and directly measure the thermophysical properties at the lander and rover and astronaut scale for the first time. We don't actually know what the thermal inertia of rocks on the moon is. When we develop these models to produce rock abundance maps from data sets like diviner, we basically assume a thermal inertia based on our best knowledge of the composition and density of the rocks. But LSIRIS will actually, for the first time, directly measure the thermal inertia of the rocks and the regolith separately, again, feeding back to the diviner data so we can produce even better global rock abundance maps from diviner. Third objective is near and dear to my heart, which is the micro cold traps question. Do these things actually exist and what are their temperatures? You'll hopefully see from other talks and posters, both during this session and even in the coming months and years, that other instruments on this same lander, as well as Viper, will directly measure the composition of these micro cold traps. But here we're interested in the temperatures. So what is the distribution and abundance of micro cold traps, given that we know that thermal gradients exist at these extreme spatial scales, small spatial scales, and that roughness increases with decreasing spatial scales. So you'd actually expect more cold traps and greater abundance at smaller scales. So getting on the surface is really key to finding all of the inventory of potential water reservoirs and reservoirs for other volatiles. And I mentioned correction of near infrared data sets that can be contaminated by thermal emission, like M-cubed. This set of measurements from LSIRIS will help with that as well. So the instrument itself has 4 bands spanning from 7.2 to 14.3 microns, including 3 compositional bands and 1 broadband channel for doing the thermophysical investigation. We'll get panoramic images around the landing site in 180 degrees. So we'll see fully one side of the landing site from 3.6 meters all the way to the horizon. And at the nearest point in our field of view, the resolution is about 7 millimeters. So we get pretty high resolution close to the lander, and then that of course declines as you move away. And we'll see all the way to the horizon, where our pixel scale will be roughly similar to the diviner footprint. And here's a rendering of the instrument, which is currently undergoing fabrication at Ball Aerospace. So I've described a little bit of the operations. Basically, we sweep plus or minus 90 degrees. Each scan takes several hours. And one of the innovative features of LSIRIS is this 3-point calibration scheme with 2 different internal calibration targets. So we get very accurate temperature measurements across a huge range of temperatures on the surface. So one of the things that we're going to look for is these roughness effects. And here's some model results showing what a dramatic difference you see in these kinds of thermal images, looking at the same surface from 2 different phase angles effectively. So with a solar azimuth of 180 degrees, with the sun kind of in a line with your field of view, you see lots of shadows, of course. And then you look at the same surface at 0 degrees azimuth with the sun behind you, and you see a lot more hot surfaces. We can quantify this with the models and then compare that to the LSIRIS data. And this will really give us a good constraint on how roughness affects infrared measurements, both in the thermal hour and all the way down to the 3 micron region that a lot of us are interested in. So we expect to get the first thermal infrared images from the lunar surface. I mentioned the thermophysical and roughness properties, and we want to link this to sample science as well, looking at the composition at these sort of nearly grain scale to compare to samples. and then understand how these micro cold traps affect the transport of water on the lunar surface. This also has implications for astronaut and rover trafficability because we can constrain the thermal inertia of these regolith finds and other hazards and including rocks and those sorts of things. So thanks for your attention.
Great. I think we have to move on to next, and you can check the chat window. There are questions for you. Ariel?
Yep, thanks. Thanks, Paul. So our next speaker is Martin Loskam, who will be presenting on a compact cosmic ray neutron spectrometer for lunar exploration missions. And we can see you, and we can see your slides. Looks good.
All right. Yeah, thank you, Ariel. And thanks for the opportunity to present our work here at this symposium, which is really great. So I'm going to present the development that we're doing currently on a cosmic ray and neutron spectrometer in general for lunar exploration missions. Just very quickly, because many of you and many excellent speakers before me have been touching on this this issue of water on the moon. So we do know that there is water on the moon that is generally accepted by now. We have signatures of water and hydrogen that were detected by multiple missions. And in particular, because we're interested in neutron spectroscopy, we are obviously looking at Lunar Prospector and at LRO here. We know that water is supposedly stable in PSRs near the poles, and that we may have some transitional presence in other areas. What we're lacking really, and this has been mentioned before multiple times, is that we have no real in situ data yet. So this is what we and other groups obviously too are working on. Neutron spectroscopy is a really powerful tool to look for water because neutrons that are created in interactions of high energy cosmic rays with the regolith do interact with the regolith and everything that is in it. So the presence of hydrogen, could be water, OH, or any other hydrogen containing material, affects the neutron energy spectrum through moderation, and basically that leads to an overall very strong effect on epithermal neutrons with respect to fast and thermal neutrons. So the relative decrease in the epithermal neutron flux is a very strong indicator for the presence of hydrogen and water. And I'm just showing those two maps down here from the famous publications of Lunar Prospector and LRO. We can really see the decrease in epithermal neutron flux at the polar regions. So we are conducting this development as part of the so-called LUVMIX project, which is a project to develop both a rover and instrumentation for the investigation of lunar volatiles. So that is a Horizon 2020 funded technology development project at this point, with the goal to do technology maturation up to TRL 4, 5, or 6, depending on the instrument and rover. It is a multinational consortium that's led by Space Application Services in Belgium. So basically the baseline assumption here is that we develop a rover and the instrument technologies that are required for a mission of 14+ days to polar regions. And the most important scientific objective is actually looking at volatiles. And there's a strong emphasis on water there. But we're also looking at the surface radiation environment, which is also of interest to our group. We do have 3 primary instruments. One of them is a drill and mass spectrometer. Then we have a laser-induced breakdown spectrometer, and then we have this what we call the Lunar Cosmic Ray Neutron Spectrometer. Just very briefly, I don't really have time to go into detail here. So basically with this rover, we're also looking at what basically everyone else is looking at. So basically landing, do a site contamination analysis, and then look into sunlit and shadowed regions, going into PSR, looking at the vicinity of large PSR, if there's any spillage of volatiles. And we have identified 6 regions of interest in a very preliminary landing site analysis, basically looking at closeness to PSR, hydrogen abundance, and things like that. And I'm just showing here on the right-hand side, you can see a example traverse that is close to Shackleton crater, actually. So obviously this is work in progress, and since we're only a tech demo right now, further studies are definitely required here. So coming to what our group is doing within that project, we call it the LCNS, so the Lunar Cosmic Ray Neutron Spectrometer, which is basically made up of two main particle detectors. One is a charged particle telescope, and that is basically used to characterize the radiation environment on the lunar surface, with a very precise determination of the angular profile as well. Also looking at albedo radiation at very low energies. And then we have a neutron spectrometer that should be sensitive to the aforementioned changes of the epithermal neutron flux. And all of that is complemented by a couple of dosimeters. And obviously, there are other instruments out there like LND, Mini-NS, and so on that do similar things. But we think that the couple of aspects that we're looking at are quite different from what others do here. So just a couple of words about the instrument design. The Charged Particle Telescope is really a very simple setup made out of silicon pixel detectors for tracking of charged particles. So those are the Timepeaks 3 detectors that NASA has been using for quite a lot of missions now. And then in between this very simple tracking telescope, we have a calorimeter made from plastic scintillators and metal absorbers. And then we have a couple additional silicon detectors for the low energy albedo measurement. And then the neutron spectrometer is made from glass scintillators, but we do have active moderators made from plastic scintillators that allow us to do an energy measurement actually in the end. And then obviously we need a veto detector to suppress the charged particle background. To give you a feeling what we're talking about, so we're aiming right now at a mass of less than 4 kilograms, size of below 3 unit CubeSat size, and then less than 15 watts max power. Those are obviously preliminary right now, but this is what we're aiming at. And you can just see here on the right-hand side an engineering model of the Charged Particle Telescope that we recently tested. So basically, the focus of this talk really is on the neutron spectrometer because that is what gives us our water and hydrogen signature. And then the Charged Particle Telescope is basically for context and background plus a general radiation measurement on the lunar surface. So looking at the performance, most of that is based on simulations with GN4 right now because we have just begun testing. And what we did, we used flat energy distributions from 10 MeV over N to 3 GeV over N to optimize a very simple cut algorithm that we have. So basically, we're looking at algorithms that allow us to do on-instrument analysis of the data with very constrained computational resources. So we used a very flat spectrum to arrive at the cuts that you see on the right-hand side here. So here you can see the spectra for different particle IDs, so different ions that we shoot onto the detector. And you can see that we can clearly separate them here for particles that have low energy, so actually stop in the detector. We use this measure of the total energy deposited times energy deposited in one particle layer. And then if we measure the total energy, so particles going through, basically we just use the total. And you can see that we can nicely separate them. So based on these very simple cuts that we have, we're looking at, and this is what we're showing here, the classification of particles. And as you can see here in this kind of matrix, basically we plot what we actually shot onto the detector in the simulation versus what our analysis algorithm predicted. We can see that for stopping particles, we can really achieve very nice values above 80% and way above 90% for lighter ions, and then for through-going particles, it's a bit worse. So we recently did tests with that at the Paul Scherrer Institute and are doing data analysis right now of that. And then as to the performance of the neutron detector, we also did GN4 simulations here, again with a very flat energy distribution between 0.1 eV and 8 MeV. So this is thermal to epithermal neutrons. And we basically defined 3 primary sensitivity ranges here that are roughly modeled after what Feldman et al. Published in their paper. So we just changed a couple of values here slightly. And what we get is what you can see on the right-hand side here. So basically, again, we do this kind of matrix plot where we have the actual energy of the neutron and then drawn against the neutron energy that we reconstructed. And you can see that in terms of classification efficiency, we achieve really, really good values here, close to 100% mostly. And then for the absolute efficiency, numbers are a bit worse because some particles, some neutrons get scattered out, some don't interact at all. But overall, we get less than 6% rejection for fast and epithermal neutrons and 100% rejection of the background. So basically, the intermediate goal is to really just do this kind of classification in these 3 sensitivity ranges. But the final goal for our flight instrument would be to do a full energy measurement, so spectroscopy measurement. So to conclude, we're currently testing engineering models of the LCNS. Like I said, analysis of the charged particle test data is already underway. We're looking at an integrated test campaign with LuVNX rover, with just a mock instrument, obviously, in September, October this year, and are close to GRL56 now, once we have completed these tests. The funding, unfortunately, will run out in the end of this year. So we're looking for potential flight opportunities if EU-funded follow-on funding should not arise. So if you're interested by what I just presented and want to know more details and are interested in cooperating with us, please reach out. You can find my email address here or find me in GatherTown. Thank you.
Okay, we need to go to the next talk now. So the next talk will be given by John Robert Brucato. The title of their talk is Water Desorption from Lunar Sample Analogs to Support the ESA Prospects Instrument Development. So John, take it away.
Yeah. Hi, everybody. So how are you? I hope you see my screen. Okay, so let me see. Move.
Yeah, we can see, no problem.
Yeah. Okay. So as you probably know, so European Space Agency is developing an instrument package that is named the Prospect. So to operate on board of Luna 27 lander from Roscosmos, Russia, and this lander is equipped by a driller that will be delivered and made in Italy. So, and it will be go to the depth at 1 meter, that deep on the South Pole lunar surface, and the grains and the sample will be extracted and delivered to a oven and the mass spec that will detect the volatiles on the sample, especially concerning the presence of water. So in this respect, a team has been set up by ESA in order to investigate the properties of the lunar soil, and with respect to the desorption and diffusion of water, and in specifically in order to evaluate the capability of the driller and the system to detect the water. And so in this respect, we have investigated in the laboratory, so the water desorption from some mineral analogs and lunar simulants, in order to quantify the sublimation kinetics of the desorption. So especially we made a temperature program of desorption experiment in which we have a ultra high vacuum chamber, the pressure inside of 10 to minus 10 millibar, in which is interfaced with a cold finger. So the cryostat can get 17 Kelvin. And so the cold finger is covered by water ice that is introduced inside the chamber by this system, in which there is a pre-chamber in which we prepare the sample, and so the volatiles, and so it's condensed on the crash. And so the cold finger is heated at a constant rate of 151 Kelvin per second, and so the water is desorbed by the cold finger and detected by a quadruple mass spec. Okay, so the temperature program of desorption, TPD, is usually a measuring of the desorption of volatiles, in this respect of water, and this is an example of the TPD curve. So there is increasing the temperature of the cold finger continuously. So we have the release of the water in the gas phase, and so the mass spec is detecting. So when all the water is released, so the intensity is decreasing again. So generally the TPD is modeled by the Polanyi-Wigner equation, in which we have the desorption rate, an exponential factor, the heating rate that we use in our experiment. This is a surface coverage. In our cases, we have just used a monolayer regime, and so we have the desorption energy here. So I'm going to show the major result. So we have made the desorption just from the naked cold finger, so that is a nickel plated copper, and after we covered the cold finger with a thin layer of dust grains of the size of 5 micron grains, and the layer is almost 100 microns of different minerals, so olivine, spinel, and statite, quartz, and the lunar simulant. And so we measured the TPD of these on these samples. So this is the case of the cold finger without any dust. And so we have the temperature of desorption of the water is 141 Kelvin. And so we can derive the desorption energy by the equation. And so when we use the olivine dust in this case, so we can see that we have a different shape of the desorption peak. So we have the main first order, the desorption of the water is occurring at the lower temperature, so it's 130 Kelvin. And so we have one shoulder in this case, and another it seems to be there. But in any case, we have for all the sample that we have measured in this case, so we have the main peak and the shoulder. So we interpreted that this shoulder has a diffusion of the water inside a thick layer of dust. So, and we have measured not only the desorption energy of the water, but also the diffusion parameter inside the layer. This is some example of what we have obtained in the lab. So again, the first major peak and the second shoulder. This is for the case of quartz, that is synthetic. So in this case, we have a very homogeneous sample. In the other, we have used the natural terrestrial minerals. And so this is the case of lunar simulant. And again, so we can see the major peak and this shoulder. Okay, going to the result. This is the whole the TPD for each sample that we have used in our experiment, so we can compare the different temperature and so on. And concluding, so we have that in general, so we haven't any major changes in the desorption temperature of water from minerals that we have investigated, included the lunar simulant too. And so we derived the energy, the desorption energy, and the diffusion parameter. So this is clearly these results are just used in order to derive these important parameter, that is absorption energy, that can be, and that is going to be used by the other team in order to evaluate the desorption of water in different conditions, because here we have used just laboratory condition in which we have a very high desorption rate, so we can model in different conditions of, for example, compared to what occurred on the moon, in which the temperature is higher, of sublimation, it seems to be higher than that derived in the lab. So this is the major results, and so thank you for your attention.
Great, thank you. I think we can jump into the discussion session. So anyway, if you have questions, you can raise your hand. I can see, and you can ask questions.
Troy, do you want to start with yours for John? Also, sorry for background noise.
Oh yeah, sure. So John, I have two questions for you, so I can ask one first. Do you think the real lunar regoliths will make any difference in comparison to the simulants or analogs used in your experiments?
Surely. So it depends not only on the macroscopic, I would say, size of the grain, but also by microporosity, so at the molecular scale. So clearly, the water can be trapped inside these mesopores or nanopores inside the real regolith, and can be released at different temperatures. So also the interaction between so the physical interaction between chemical physical interaction between the water with this structure can be really different. So surely, so it's really important to have the real regolith. So we are just working in that respect in order to have a real sample to be used in this experiment.
Great, thank you.
And the second question I see for the publication, so we are just working all together to have a publication. Yes, so the answer is yes. So it will come in the next month.
That would be fabulous. Can't wait.
Great. Anyone has questions for our speakers in this session?
Yeah, so I had a question for John, the nice talk on TPD. So there was a curious shift for the ice peak to lower temperatures when you had the grains. So I wonder if the grains are hydrophobic, which would give you a lower temperature. And then the width could also be correlated with a different binding energy distribution of defect sites as well as diffusion. So diffusion for sure is important, but the binding site distribution may matter.
Yeah, concerning the second part of your question, so I know your work, and so concerning this respect, so the fact that we have this second bump, the second peak at higher temperature. So I think you are right. So it could be due to the fact that there are different active sites in the sample that can trap the water. But in any case, so I think that the fact that this second bump is just one band, how can I say, so just one bump, not many of these. So it's mostly, to me, related to the diffusion of water instead to the fact that there is a other active sites, because in general for minerals the active sites are few, so it's not really a lot. So in this case I would expect to see many bumps, each of them correlated for each different band energy. Concerning the first part of the question, so I think the main is not just the fact that this is hydrophobic, the dust. So it's probably due to the fact that the binding energy and the process of absorption in the case of nickel plated cold finger is different. So the energy is just higher than the dust grains. So this is what we interpreted the result. So the main reason, not really depending on the fact that is hydrophobic.
Great, thank you, John. I saw a comment from Parvati. She's asking, like, since we've done a lot of work about lunar materials, lunar-like materials across the board, so she's asking, is there a database that compiles all the results, like in previous experiments? I saw Michael has comments. He said right now it's still pretty small. Anyone knows there's such a database?
I haven't heard of a database, but that would be great. I also think there's probably a lot of research into like desorption for different materials, not in like a planetary context, but like in an industrial context. I've delved a little bit into literature like that, doing my own research, and it can be quite helpful. So finding a database where information like that would be fabulous.
Yeah, totally agree. I know Tom Armando has done a lot of work using lunar materials or simulants. Not sure he has a database.
I wouldn't call it a database, but we have a lot of data, and we have done data or measurements on real lunar material. And to answer your question, it does look pretty well. The correlation with the simulants, TPD from simulants and TPD with real material looks pretty good, providing you use the material from Dan Britt. If I use JSC1A, that's not true. So it really depends on your simulant.
Okay.
In our case, it's also the same simulant for Britt. So yeah.
Yeah, John, I'll send you this data so you can see it. It's actually a pretty good correlation.
Okay.
Yeah.
Okay, great.
Yeah.
Who do you talk to if you're like, NASA, we need a database? Who does that? The PDS? I don't know.
That was actually a question asked at a recent spectral meeting as well. So I think that's a to be determined question.
I'm glad I'm not the only one with that on my mind.
Yeah, there are a lot of like spectral database regarding like a visible to like even far infrared.
Right, but they're spread out around the world,
Yes.
around a bunch of different websites. There's no like PDS equivalent where you just go to one node for everything you need.
Yeah, I know Relab is joining PDS, so they are developing a portal. You can search what you want.
That is actually exactly what brought this into my mind, was Relab's recent transition into the PDS and just how useful that has been. And like wondering, because I know that there are PDS nodes for missions and instruments, et cetera. But if, there were also like important quantities that could be collected from various studies and put in one place, that would be like a fabulous PDS resource. But I don't know if that's how PDS like funding works.
There are some comments in the chat regarding PDART.
Yeah, I think that's pretty clearly within the purview of the PDART program. So whatever that stands for, Planetary Data Archiving and Research Tools.
Remember that acronym.
This is Alex. Just a quick note. It just came across my desk recently. There's a new database that's being built. It's called Astromat. It's all kinds of, it should focus on lunar stuff, but probably more than that. So maybe that will be one in the future we can go to and people submit. We can pull out all the data from there. So potentially.
That's great. Thank you for sharing the link, Alex.
Ooh.
Any further questions? Can I? Okay, I'm the chair. Okay, I can. So Paul Hein, I have another question to ask. Is it possible to use ARIS to discriminate like a buried ice from like buried rocks?
Oh, wow. I think if we had like a year-long mission, maybe, but with the short, 14-day duration on the surface, during sunlight hours, I don't think we'd be able to discriminate between buried ice and buried rocks. Especially because I think the temperature response at the surface would be very similar, given the uncertainties we have in the configuration of the ice and its density.
Okay. Hopefully your mission can last longer.
Yeah, I'm hopeful that in the future, we can deploy radiometers like this for much longer missions.
Mm-hmm.
And Matt Sigler and his group have been doing a lot of good work looking at the use of longer wavelengths or lower frequency measurements in the microwave range to look directly at the both the thermophysical and dielectric properties in the subsurface, since that's another sort of independent technique to sense in the subsurface.
Is there anything new on the microwave stuff? Do you know, Paul? Because I remember seeing it at LPSC a couple of years ago, and it was mind-blowing a little bit. But I don't know, with the pandemic and everything, I've kind of lost track of what's going on there.
Yeah, I would suggest starting with the papers from Fong. It's F-E-N-G, Jianqing Fong. So he does. He's been working with the MWR data from the Chang'e orbiters, and just sort of branching out from there. There's been numerous publications from that data set in the last couple of years.
Awesome.
Paul, Lucy had asked a question to both Shuai and Miriam, and I just wanted to give Miriam the chance to also answer if she wanted to. But Paul had made a comment about how ice regolith grains would be very short-lived. Of course, ice cobbles would persist much longer. And just asking Miriam if you had anything else you wanted to comment in addition to Shuai's response.
Yes, thank you. Well, we're really looking forward to be able to analyze the variation in time that we can potentially see with the SP data through the about 1.5 to 2 years of acquisition. So yes, we're certainly going to be looking at specific places. If we can see changes in time, then we'll look in that direction. Yeah.
So Ariel, I have a question for you. What kind of like a resolution when you say like roughness? The moon and the Mercury, are they, the same scale resolution, or is different regarding to the roughness?
What I presented today was almost similar resolution. So 120 meter for the moon and 125 meter for Mercury. The coarser resolution, sort of like those larger scale variations you're seeing. So the results are like hectometer scale roughness. Yeah. If the DEMs are different scales, it doesn't really make, yeah, you can't compare because you're looking at different topography variations.
Okay, thank you.
I was also just going to add, Shwai, another thing is like, even with higher resolution DEMs are available for the moon, theirs are based on higher amounts of interpolation. And so being able to look at the roughness at the 120 meter scale allows for these measurements to be made on actual LOLA pulses, which also is important for this measurement. And I think Elizabeth has a comment, and then also Paul Hain put in some paper links for the microwave data in the chat. So thanks, Paul.
Yeah, Elizabeth, do you have a question?
Ooh, yes. Well, it's like kind of a very specific question. Following up on the one I asked you earlier, I'm super curious about looking at those plots again, where you were looking at the 2 micron band depth versus the ice abundance. And remind me, was that like physical ice mixed with regolith, or did you mix water in, or?
Yeah, it's physical ice sieved into 63 to 75 micron, mixed with analog, a marble glass, and also at the same particle size range. So the mean particle size is around 70 micron. So physically mix them together independently and then measure the spectral at a standard viewing geometry, 30-degree incidence, 0 impedance, and a 30-degree phase angle. And also you can see I did a simulation using the radiative transfer model to mix ice with the different Apollo samples and also the analog. It's very interesting to me. Is like the whole trend won't show any like a compositional dependence, and also won't show any like a maturity dependence, because Apollo 11 is more mature than Apollo 16 samples, so they all follow on the same trend.
Yeah, I mean, that's what I'm really curious about, because obviously that's a good place to start with ice particles and, you know, regolith particles that are a similar size. But I had noticed kind of towards the lower end of your graph, if that, I can't remember if that was lower band depth and lower abundance, your trends kind of started to deviate in an interesting way, to me at least. They didn't just scatter, they seemed like they were kind of following some sort of trend.
Yeah, you're absolutely right. Yeah.
Yeah.
That's because the absorption of the host mineral, host regolith. Yeah, you're right. But the different, you know, the deviation is kind of small in comparison to the whole trend, the scattering of the whole trend.
Yeah. Oh, wait. So what exactly was causing the deviation at the low end of the graph?
So the Apollo 16 sample and also the marble glass I use show a 2 micron absorption feature. So it's kind of like overlapped with the water ice absorption. That will, you know, because the 2 options overlap on each other, you can overestimate the absorption depth. So that's give you the deviation. But, you know, we know on the lunar surface, the 2 micron absorption are typically much weaker than the 1 micron, and most of them are featureless. So yeah, even though it has effects, but the effects is small.
Yeah. So I wonder, with like the lack of the compositional dependence, do you think that could be related to the fact that the ice is either it's just brighter or more transparent to a degree where you're just over printing the variations from like the much darker, like overall darker regolith entirely? I'm assuming that both the samples you used, like they were both lunar, correct?
Yeah, I think you're right. Maybe because the ice absorption is much stronger. It's very strong absorber, right? In the IR, in IR region. So and also the environments I use, the regoliths I use are normally featureless in 2 micron. I think that's the reason why we don't see a compositional dependence. So I'm going to use like some maybe pyroxene samples to see. I would imagine it will show a strong deviation.
Yeah, that's super interesting stuff. And I mean, I don't want to monopolize the conversation here, but I'm curious to see what will happen when you start varying the particle sizes a little bit more and have different particle sizes of like ice and like regolith, for example.
Yeah,
yeah,
we're doing the work now.
Cool stuff,
Thank you.
dude.
Thanks.
Thanks, Elizabeth. Those are good questions. There's also one more for Shwai and Miriam from Parvati in the chat, asking if you've thought about using M-Cube and Kaguya SP data to look for non-water volatiles.
Not yet for SP. That was really a first preliminary look, and I was really surprised to see how good the data looks. So it's something that we can definitely do in the future.
Yeah, so that's really a good question. So I talked to, I discussed with Norbert a long time ago, since he's doing the work to map the carbon dioxide region in the lunar PSRs. So when I saw his map, I feel like, oh, the region is too small to average enough M-Cube pixels to reduce the noise to see the real features. In addition, the CO2 feature in the visible to, particularly in the IR region, is too sharp. So normally I think less than 20 nanometer or less than 40 nanometer. Well, that's the spectral resolution of M-Cube data. So the spectral resolution of M-Cube data may not be sufficient to discriminate like a CO2 as at least. Yeah, we need more data, particularly for PSRs. That's a big gap currently, I feel. Fortunately, we will have more and more mission to the polar region. So Ariel, Paul has a question for you.
Sorry, it's super loud here, so I'm going to respond in the chat.
Where are you?
I saw it.
I mean, if there aren't any more questions right now, maybe Ariel could regale us with the latest and greatest on Viper, the drama of the mission.
I would love to hear.
Yeah.
Oh.
Ooh.
So like, what instruments are you most excited, this is a question, Ariel, to see developed to the surface of the moon this decade?
Yep, sorry, it's a little quieter. Parvati and Caroline suggested we put together a poll so you can go to this website and hopefully type in the code and answer. Hopefully this works and it should update real time.
So is this an instrument that's in the pipeline or whatever instrument we can imagine?
Whatever you want. It's just for fun and to get a pulse of people's thoughts.
I feel like I'm biased because I want to send my own one to the moon. So
I'll vote for humans.
I'll vote against humans too soon.
Why?
Humans are really, really gassy and take bigger spacecraft. I want to see it as it is before we see it as humans have turned it into.
And poorly designed machines that degrade over time.
I feel like we could have a whole discussion about whether humans are poorly designed or like incredibly designed.
I'm just joking because I'm feeling I'm aging and I can't reverse it.
Oh no. I was
That's-
thinking along the lines of like, you can remove a kidney from a human and the human is still functional. I'm trying to think of a robot where you can just pull a part out of it and it's like, nah, I'm good.
There's plenty of stuff designed with redundancy.
Okay, well, I don't see any other questions in the chat, but yeah, I think we should thank everyone that contributed today, and also a huge thanks to Ricky and everyone for technical support. I'm sorry, it's so loud here. I'm gonna mute.
Yeah, I think, yeah, we want to thank everyone for participating in this session. We definitely had a great time, great talks. And also, we want to thank Ricky for the technician work, make the session went so smoothly. And if we don't have any further questions, comments, I think we can end this session and let our European folks have a good sleep. And both me and Ari, we are located in Hawaii, so we got up at like 4 o'clock in the morning. Yeah, so I also need a rest.
Time for bed, man.
Yeah.
Enjoy.
Thank you. Okay, so see you, everyone. Thank you again.
Thank you.
Bye, everyone.
Recording stopped.